Dr. Sartajul Hassan. He is a faculty member at IIT Jammu. He did his PhD in IIT Bombay in the year 2010. And he's one of those rare PhD students who got a job even before he got his PhD. So he was working with DRDO, the Defense Research and Development Organization of the Government of India, I think from 2007. And then in between, he also did a postdoctoral fellowship at Carleton University in Ottawa, Canada, with Daniel Panario and Steve Wong. And he returned to DRDO and then decided that he would much rather be in academics than proper government, as it were. And he found himself a job at IIT Jammu, and he has been there. He was, I think, until recently, I'm not sure he still was the Associate Dean of Faculty Affairs at IIT Jammu. And he specializes in algebra and cryptography, especially linear feedback shift registers and related things. And today he will talk to us about introduction to stream ciphers and LFSRs, or linear feedback shift registers. Sartaj, please.
Okay. Thank you, sir, for your kind introduction. So as you can see, the title of the talk today is Introduction to Stream Ciphers and Linear Feedback Shift Register. So in fact, there are two talks based on this. Another would be on Thursday. So today, I would primarily try to introduce what are stream ciphers. And it's a very elementary, actually. The talk that I'm going to give is sort of very elementary. And my apologies in advance for those who already know this stuff. And, there are, of course, in audience, there are crypto experts. But my motivation for this talk is, I want to introduce this topic to those who have not heard of this before. So it's going to be very, very elementary and very, there is not going to be, much mathematics in this lecture. But of course, in the second lecture, I will talk about, mathematical theory of linear feedback shift register, those stuff. But today, it's going to be very elementary. So, okay. So let me begin. Okay, so here is the plan of my talk. So I will introduce what is called stream cipher and what are the random number generators. And then if time permits today, then I will also speak about linear feedback shift registers. Okay, so yeah, so Swarma, what is cryptography? We are living in a digital world, and we want to communicate secure with our loved ones, or even professionally or personally. So we want some sort of security, measures so that we can communicate securely. So one of the main tasks in cryptography is secure communication, unlike, of course, coding theory. And there are four major goals in cryptography. I'll just quickly go through it. The first major goal is privacy, also known as confidentiality. So that means if two persons are communicating over an insecure channel, then that message should not be understood or read by any third person except the intended persons. So that means we want some sort of privacy or confidentiality in our message. We also want authenticity. So authenticity means, the message has been originated from the correct source, and it also is going to the correct source. So, as most of you may know, that Alice and Bob, they are two standard people in cryptography. So if Alice and Bob, they want to communicate, so they have to authenticate each other. Like, the message is exactly coming from Alice. So that comes under authentication. And also the integrity of the message. So integrity means, somebody has not really altered the message while it is going through the insecure channel. So that is also we have to ensure as part of cryptographic goals. And then non-repudiation. That means, we should be prove in the court of law that, the message has been originated from Alice. So that also to be ensured. And of course, there are various schemes like digital signatures, digital certificates, and so on. And that involves, public key cryptography. So in a nutshell, so the cryptographers try very hard to achieve this pain. If you just look at this first letters P, A, I, and N, so they try very hard to achieve this pain, which is at times becomes quite painful due to the active presence of cryptanalysts in the cyberspace. So these are four major goals, of cryptographers. So we want to ensure all of these things. Okay, so now just briefly, of course, in today's lecture by Panteleimon Stanica, he has already told what is symmetric key encryption. So I'll just give the pictorial view. I'll not go into it. So symmetric key symmetric key encryption means for enciphering and deciphering, you actually use the same key. Quite similar to this lock. In order to lock this, you need locking and unlocking is being done by the same key. So that's sort of symmetric key encryption. So beyond that, I will not go into the details. And symmetric key encryption, can be categorized into two parts like symmetric ciphers and block ciphers. So today, the last talk is by Panteleimon Stanica on block ciphers. So he would be telling you about various kind of block ciphers like DES, AES, and various modes of functioning of those block ciphers. However, I will rather focus on stream cipher. That is also part of symmetric key encryption. Of course, there are various issues in symmetric key cryptography. For example, the key management is the biggest issue. And in order to address that, we have what is called asymmetric key encryption key, asymmetric key encryption schemes, mainly public key cryptography. So, the pictorial view of public key cryptography could be something like this. If you have this kind of lock, so, in order to lock it, you just need to press this. It gets locked. And in order to unlock it, you need a key. So, for enciphering and deciphering, there are two different keys that are being used. For encryption, you use one key, and for decryption, you use another key. However, those keys may be related somehow. So, like in RSA. So, famous examples of public key cryptography are RSA, and there is a talk today by Shantanu Sarkar, who would be speaking about public key cryptography in detail today. Most likely, he will cover the things like RSA and maybe elliptic curve cryptography and maybe more. So I am here. So I want to do stream ciphers today. So, as I told you, so here is this cryptography, and it has got two parts: symmetric and asymmetric. And here we have symmetric cryptography, and this has got two parts actually, namely block ciphers and stream ciphers. So block ciphers, they will be covered by Pante, and this is where I need to focus today. Okay, so by the stream cipher is such a beautiful name that by name itself we know what is an stream cipher. So basically, what happens in a stream cipher, the encryption, we have a message, and that message can be converted into bits of zeros and ones. So we have a string of zeros and ones, which is my message. So the encryption is done, bit by bit. So every bit is encrypted, unlike the block ciphers. In block ciphers, we don't encrypt, each bit one by one. Rather, we encrypt block of bits. Like, 128 bits we'll encrypt at a time in AES, or maybe 256 bits at a time in AES. So AES is a block cipher. So unlike block ciphers, we will encrypt here, in a bit by bit fashion. So here our battleground is this field, binary field, F2. So there are only two elements, 0 and 1. And how the addition and multiplication is being defined. So 0 plus 0 is 0, 0 plus 1 plus 0 is 1, and 0 plus 1 is 1, 1 plus 1 is 0. So we are adding and taking modulo 2. So it's a modulo 2 arithmetic. So 1 plus 1 is 0. So this is the arithmetic that we are going to use. And this is the simplest field, smallest field and simplest field. And this operation is basically XOR operation. Those who are from electrical engineering, they would know this is the nothing but XOR gate, basically. So this is something, electrical engineers use, this XOR gates. And so this is the arithmetic we will consider. Okay. So as I told you, the encryption is being done bit by bit. So what is the model of stream cipher basically? So let me draw a picture. So encryption algorithm, it's very simple in stream cipher actually. How the encryption is being done. So before that, let me tell you some more definitions. Maybe already you are aware. So here, there is some encryption algorithm. That uses some key. And here is my message. And then it goes to insecure channel. Here I have, decryption algorithm. Again, uses either same key or different key depending on what we are using, a symmetric key or symmetric key. So I'm taking symmetric key encryption. So same key is being used. And here we get the original message. So this is called actually, the original message is usually known as plain text. And the message that is going, this message is going encrypted by using this algorithm. So this is known as ciphertext. These definitions have been also told by Panteleimon Stradeva. I'm just trying to recall. Here again, you are getting back your plain text. Okay. So this is the usual, model of cryptographic algorithms. Now, I'm just trying to tell you how the encryption takes place in stream cipher. It's a very simple, fairly simple algorithm, unlike public key cryptography and block ciphers and so on. So encryption algorithm is too easy, So how does it take? Suppose I have my message bits. Suppose I denote by, X0, X1, X2, and so on. These are my message bits. So that's I am trying to send. And here are my key bits. This is my message. So key bits, basically, I will denote by S0, S1, or maybe I should write horizontally. S0, S1, S2. We could have used K0, K1, K2, but I'm using with the purpose because I have to define the linear feedback shift register where I will use this notation S0, S1, and S2. So I'm using this notation. And then what you do is, so SIs, basically, they are coming from your field F2. And XIs are also coming from your F2. So these are my key bits, actually. From where they are coming, let's forget about it right now. So these are my key bits. So the encryption is done, in a very easy way. So you just XOR these bits, So you get, X0, you XOR it with the S0, you get your ciphertext bit Y0, let's call it Y0. Similarly, Y1 is being obtained by X1, XORing with S1. So this is how you get your cipher. So here is the sequence Y0, Y1, Y2, and so on. So this is your ciphertext. Now, in order to decrypt it, again, decryption function is also very easy here. Again, you XOR it with the same key. The same key is being used here. So let me draw this arrow. So I'm using the same key, S0, S1, etc. And I'm adding now this, so this is how it is being done. So I will obtain X0 by just adding Y0 plus, this is the XOR operation, S0. So why does it give me X0? It's fairly simple because Y0 is nothing but your X0 plus S0 plus S0. So this is nothing but X0 plus 2 times S0, and of course we are in the binary field F2, so this will be 0, so you get actually X0. And similarly, you can obtain your X1 equal to Y1 XORing with S1, that will give you X1. So this is how you obtain your message. X0, I think this is little thick, so let me just erase the thickness actually. Okay, maybe this is better. X0, okay. Yeah, X0, X1, X2, and so on. This is how you get. So this is the basic model of the stream cipher. Now the only point is from where these key bits are coming. So that is something we will discuss about, and what properties they should have. So that is the main content of stream cipher, how to design this key stream generator. So now now the name stream cipher, that must be clear from this picture. So your message bits are streaming on one hand. On the other hand, your key bits are getting streamed. And then you are just XORing them. So X0 with S0, X1 with S1. And for decryption function, that is also quite easy, that you are just XORing your cipher text with the same key bit string actually, S0, S1, etc. So they have to be these two, they have to be synchronized actually. Encryption function and decryption function. So the same generator should generate the same key stream actually. So this is how the model of stream cipher works. Now let's look at some easy observation about this stream cipher. Let's look at, suppose my message is I write here my message bit. So YIs are basically cipher text and XIs are message bits, and SIs are key bits. And here is my key bit, and here is my cipher text. Let's try to analyze this further. So suppose I have my bits 1, message bit 1, 0, 0. Here I have 1, 0, 1, 0. And what is going to be the cipher text, corresponding cipher text? XI plus, so 1 plus 1, that will give me 0. And 1 plus 0 will give me 1, 0 plus 1 will give me 1, 0 plus 0 will give me 0. So now let's try to understand what is happening actually in stream cipher. So if you look at this, this bit 1 and 1. So the 1 can get encrypted to either 0 or 1 depending on the key bit. If the key bit is 1, then 1 gets encrypted to 0. If the key bit is 0, then 1 gets encrypted to 1. So any message bit that can get encrypted to either 0 or 1. Similarly, if you look at this 0, 0 can also go to either 1 or 0 can go to 0 depending on the key bit. Okay. So you see that, so in order to make it, this encryption secure, you must have realized, this sequence must satisfy some very unique property. For example, suppose if my sequence bit is just 1, 1, 1, 1, 1, for example, all ones. If there are all ones, then 1 goes to 0, and again 1 goes to 0, 0 goes to 1, 0 goes to 1. So, so given the cipher text, it is difficult to, if your this sequence satisfies certain property, that you can guess that that property has to be somehow randomness. So given a cipher text bit which is 0 or 1, it will have 50% chances that the probability that the message is either 0 or 1 depending on the cipher text is going to be just half if your the key bits are random bits. Other thing you would observe that if your key bit is 1, then this bit becomes 0. If key bit is 0, then 1 goes to 1 itself. So it means that if your key bit is 0, then your message goes as it is. It goes in plain actually. Your message bit goes in plain. So 1 will go to 1 itself, 0 will go to 0 itself. And if your key bit is 1, then the bit gets flipped. So it's very interesting, this encryption. If you look at the picture again, so what is happening is this picture again, if you look at here. So if my key bit is 1, then this bit will become, X0 will become 1 here. And again, while decrypting, it will again become 0. If my key bit is 1, and suppose this bit is 1, then 1 plus 1 will give me 0. Again, this gets flipped, and again it will get flipped. So if the key bit is 1, then the message bit gets flipped, and if the key bit is 0, it doesn't change actually. It goes as it is. So it's a very, very simple algorithm, this encryption and decryption. So the main security lies basically how random the key is actually, the key stream is. If this key stream is a random sequence, then it turns out that it's fairly secure and it can be used. And in fact, we are using it in our day-to-day life. For example, our mobile phones, GSM mobile phones. So they are using a stream cipher called A51. So this is the stream cipher A51. This is being used in GSM mobile networks. So by the way, this consists of 3 LFSR, this cipher A51. Of course, I have a picture of this A51. I will show you at the end of the slides. How does it look like, A51? So A51 is the stream cipher that is being used in our day-to-day life. We are using it. And okay, so as we noticed that if the key appears to be, if key is random string of bits, then this encryption and decryption scheme is secure. If it has a pattern, for example, you have 10 zeros, then 10 ones, 10 zeros, 10 ones. If this kind of pattern is there in your key stream, then 10 bits, if there are 10 zeros in the beginning of the key stream, then your 10 bits, message bits will go in plain. And if 10 ones are there after 10 zeros, then your 10 bits will get flipped. So the pattern will be visible. So the pattern of, if the key is not random, it follows certain patterns. So your ciphertext will also follow some pattern, and therefore it will help attacker, to guess either the exact key or maybe the message bits. So therefore, in order to have this scheme to be secure, it should have the key stream has to be random. Now we'll little bit talk about randomness. I would also like to mention here the content of this slide that I have taken from 2 books basically, one by Extension and another by Christoph Parr. So these 2 books I have followed here, and the pictures are also taken from these books actually. Okay, so now, so this is the model I already told you. So this is the model of stream cipher. Now, okay, now I'll just talk about a little bit of stream cipher. I kept some slides blank in case if I have to write something. So sorry about that. I thought maybe some question comes, I can, just, okay. So now let's talk about this random number generators, because we need something, random key stream. So we can categorize into 3 parts. So there are 2 random number generators. So 2 random number generators, they are characterized by the fact that their output cannot be reproduced. So for example, if you have a fair coin or a fair dice, unbiased coin, then if you, just flip it, then if head comes, write 1, if tail comes, write 0, and flip it, let's say 1000 times. So you will get a string of length 1000. It's a random string if your coin is fair. But the problem with this, suppose I use this string for my encryption. This is a random string. So if Alice uses this string, so of course she can encrypt the message by XORing it with the the message that she wants to send. But this sequence of bits cannot be recreated again. Bob cannot recreate this sequence because it's a random, truly random sequence. Even if he flips the coin again 1000 times, he may not get the same sequence. So therefore, true random number generators, that will not help us actually in some sense, in designing good stream ciphers. So anyway, so the true random number generators, they are based on the physical processes. For example, flipping of coins, rolling of dice, and semiconductor noise, and so on, and movement of the mice and spin of the hard disk, and so on and so forth. Now there comes another kind of generator that is called pseudo random number generator. So pseudo random number generator, they are basically sequences which are being computed by some initial value or initial seed value. So typically a pseudo random number generator would look like this. They will be following this. So we have S0, which is the seed, and then we have some function, and recursively we generate other members of the sequence. Si plus 1 is given by f of Si. And here is the generalization of this. So this is how we generate the pseudo random number generator. And the example of pseudo random number generators, the famous example is linear congruential generator. So it takes S0 equal to, this is the seed value, and you take Si plus 1 equal to ASI plus B modulo M. So where these SIs and AIs, I'm taking them to be in the ring Zm. So they are all integers. So if you use this recurrence relation, we can get a pseudo random number generator. And the example of this kind of generator is the language, the NCC. So they have something called rand function. So they use this kind of generator. So it's a very special value, seed value, 1, 2, 3, 4, 5. It's your seed value, and then you get this. And M is also very special, 2 to the power 31. So this produces a pseudo random number, pseudo random sequence for many practical purposes, actually. But not all pseudo random number generator will be useful to us as far as cryptography is concerned. We need to have one extra condition. We don't want any kind of pseudo random number generator. By the way, pseudo random number generator, there are various kind of pseudo random number generators available in the literature, but not all of them can be used in cryptography. In fact, they are being used in various other applications like software testing and so on. So there, one requires pseudo random numbers. So they are being used. But for cryptographically, we require a cryptographically secure pseudo random number generator. So this is what it is: cryptographically secure pseudo random number generator. So what we mean by cryptographically secure pseudo random number generator, it should have one additional. It has to be pseudo random number generator, but also it has to have one additional property. So informally speaking, this means that given n output bits of the key stream, it is computationally infeasible to compute the subsequent bits. If you have n bits, it should be computationally infeasible. So in other words, we can also say that if you are given n consecutive bits of the key stream, so there is no polynomial time algorithm that can predict the next bit with better than 50% chances of success. So this additional property has to be there in any pseudo random number generator that we want to use. So this is about cryptographically secure pseudo random number generator. Now I will just briefly talk about what is called one-time pad. So what is one-time pad? I already told you. If you take your key stream generated by a truly random number generator, for example, flipping of coins, so that will give you truly random number, truly random sequence of bits. Okay, so if I use that as a key, then your stream cipher is known as one-time pad. And once you have used this key, you cannot reuse it again. And another thing is that the key should be as long as the message itself. So there are 2-3 properties that it should follow. So one-time pad, basically here is the definition, a stream cipher for which the key stream S0, S1, S2 is generated by a true random number generator, and the key stream is only known to the legitimate communicating parties. By the way, this is also a problem, the point number 2. because you have a random sequence, truly random sequence. How can we give it to the person whom we want to communicate? How to transport that key to that person? So it's a big problem, because he cannot reproduce, because it's coming from physical process. He cannot recreate the truly random sequence of truly random bits. So that's a problem. And every key stream bit SI is only used once. We cannot use twice for encryption. So these are the few points when a stream cipher is known as one-time pad. And it turns out that it is perfectly secure, this stream cipher. Even given infinite computational power or computing power, you cannot break this cipher, one-time pad. And this was proved by Shannon in the year 1949. In fact, this one-time pad was, it was invented by Varnam in 1970, if I am not wrong, and people believed it to be perfectly secure. It cannot be broken, but there was no mathematical proof unless in 1994 Claude Shannon gave a formal proof of this, that it cannot be broken. So it was proved by Claude Shannon that this one-time pad, in short OTP, has got perfect secrecy, or it is perfectly secure. It cannot be broken, even having infinite computing power. So what does it mean? Perfect secrecy. Informally, it means that eavesdropper cannot obtain any information about the plain text by observing the ciphertext. He will not have any information. So this can be, formalized. So what one means by a perfect secrecy, a crypto system has perfect secrecy if the probability that the plain text X was sent and the ciphertext, given that the ciphertext Y was obtained, is same as the probability that X was sent. So, the message space, the message comes from a message space, and we have ciphertext space, plain text space, ciphertext space. So each message may have some probability. It will have, some probability of occurrence in that message space. So it says that, given that you observe that, the ciphertext is Y, the knowledge of ciphertext does not change the probability that the message X was sent. So if any crypto system satisfies this property, and that should be true for all X in the plain text space and Y in the ciphertext space, if that happens, then we say that the crypto system is perfectly secure. So this is what perfect secrecy means, irrespective of what is the distribution of the message in the message space or plain text space. So that has to be true. This is called perfect secrecy. So let me see how much time I have. Okay, I still have 25 minutes. So I think I'll not go into the proof of it, but I have written down the proof. Maybe I'll just give you a brief idea about the proof. So mathematical proof of perfect secrecy of one-time pad. So Xi is your ith plain text bit, Yi is ith ciphertext bit, Ki is ith. I should have used Si basically here. Anyway, so maybe did I use Si later? Yeah, I think it's maybe you can say it Si. Si is the ith key bit, and here is the mixing algorithm that this is how you obtain the ciphertext. Yi equal to Xi plus Si, and this denotes Pxi denotes the probability that Xi was sent, and probability that Xi was sent given that Yi was observed. So these are the notations, and we want to show that this is perfect. This has perfect secrecy. So that means we have to show that the probability that Xi was sent is same as probability that Xi was sent given that Yi was observed. So that means that this is a very fundamental equation, and this tells that that means that ciphertext gives us no information about the plain text, if this holds true. So in order to prove that, first I think I'll just briefly mention that the probability distribution of the ciphertext is also uniform, random. So the probability that yi equal to 0 was observed, or yi equal to 1 was observed, that remains half. Because I'm using one-time pad is we are using the truly random sequence. So the probability of occurrence of 0 or 1 is exactly half if it is a truly random sequence. So the probability that Si equal to 0 is half. Probability that Si equal to 1 is also half, exactly half. So it turns out that if you are using the true random sequence, then this ciphertext bits that you would receive, they will also follow. That is also going to be truly random. The probability of each ciphertext bit is going to be exactly half. So that is one step that one has to perform. So here, this is what this yi is the ciphertext. So this is also uniform. So this is what the proof is. The probability that yi is 1, that can happen if the plain text is 0 and your key bit is 1, or your plain text is 1 or key bit is 0. But this probability is half. This probability is also half. So I can take this out. So what remains is probability that xi is 0, probability that xi is 1. But this probability, whatever the probability is, probability that xi is 0, we don't know what is the distribution of how the masses bits are being distributed. So whatever the probability is, this sum is always going to be 1. So we get exactly 1. Similarly, we have to compute this, we get this. And then we also show that the probability that yi was observed given that xi was sent, that is also uniform distribution. And that also one can show. And then by using Bayes' rule, that is coming from probability theory, one can prove that this is the Bayes' rule basically. This is the probability that xi was sent and yi was observed is same that probability that yi was observed given that xi was sent, and this is probability that xi was sent and yi was observed. So they are same actually. That comes directly from Bayes' rule. And of course here I am assuming that the probability of xi is positive, probability of yi is positive. And then this we have already proved that ciphertext distribution is uniform, and this distribution is also uniform, means probability is half. By using this we can prove this. So it turns out that this OTP is perfectly secure. It has perfect secrecy. This notion was introduced by Shannon. So in view of Shannon's notion of perfect secrecy, this one-time pad is unbreakable. But it is highly impractical. We cannot use it in practice because the key size is as long as the message itself. How to transport the keys to the other person, because it's a truly random sequence, and the receiver cannot reproduce these bits. So they have to be transported in a secure way. So what is the point to transport such long keys in a secure way? Rather, we can transport the message itself in a secure way. So it's impractical actually. And also how to generate truly random bits, that's also a problem. So it's not practical actually to use OTP. It's not practical at all. We cannot. So therefore, we need some approximation of OTP, one-time pad. So the approximation means we need to have some key sequence which is not truly random but appears to be random, and and given any n bits, it is infeasible to compute the next bit. With that property, we need some key stream generator. So there comes actually this LFSR linear feedback shift register will come into the picture. So now I'm going to introduce what is called LFSR. But before that, so the stream ciphers are of two types, namely synchronous stream cipher. So that means the key stream depends only on the key. It doesn't depend on anything else. And asynchronous stream cipher, That means key stream depends not only on the key, but also on the cipher text. And most of the practical stream ciphers, they basically are synchronous stream ciphers. So, this becomes synchronous stream cipher. But anyway, I will focus on synchronous stream cipher, where key depends only on the key actually. So, this is the basic difference between synchronous and asynchronous. So, if here you look at, we have this key, with the help of shorter key, we will generate a longer key by using some key stream generator. So this key stream does not depend, it depends only on the key. So this is called synchronous. But if additionally this arrow is also there, that means this key depend on key as well as the cipher text bits. So this becomes asynchronous stream cipher. So we will focus on synchronous stream cipher. Okay. So here is the model of the practical stream cipher. This is how it should be. So we will start with the initial key, which is going to be shorter key. And with the help of shorter key, we will generate a very long key. And in a way that it looks like random. It is, of course, cannot be random, but it should appear like a random to the attacker or eavesdropper Oscar. So here is this Alice. So this is the model. We will have a key stream generator, and this is the message bits. You are XORing them to get your cipher text. And again, the same key stream generator is here. And again, the same key bits are being generated. And we are able to get the original message. So this is the practical model of the stream cipher. Okay, very good. So let me see the time. Okay. Yeah, I still have time, it seems. Okay. So now I'm coming to linear feedback shift registers. Okay. So what are linear feedback shift registers? And then maybe in the next lecture, we will develop some mathematical theory of linear feedback shift registers. So, so the background is clear. We want to generate a pseudo-random sequence, which is cryptographically secure. That means given, n bits, it is, we cannot predict the next bit. So that is what, and for that, we are going to use what is known as linear feedback shift register. So the word register, that comes from electrical engineering actually. So the registers are, they are sort of flip-flops. So they store the information either 0 or 1. So suppose I have 3 flip-flops. I will take a linear feedback shift register of length 3 only at present. So they can store some information, either 0 or 1. So, these flip-flops, in one clock, if we clock it, they shift the values of that are stored in the flip-flops. So for example, let's say in this, I have, let's say, 1, 0, 0. So here the bit is 0, here the bit is 0. Of course, this electrical engineering will understand it better. So that means it is basically analog signals and so on. So of course, I don't know those things, in a deeper details, how these are being stored. But anyway, so for us, the flip-flop is just like a box where I can put either 0 or 1. 0 or 1. And if you clock these, so then what happens is, this bit, the output of this flip-flop is 0. This will shift here. And output of this flip-flop will shift here. And the output of this flip-flop will shift here. So if I shift it, here I will get 0. Okay. And this gets shifted over here in one clock. So in place of this 0, I will get this 0. And this gets shifted over here. So here I will get 1. And this remains empty. There is nothing here, this cell. So in one clock, so 0 gets shifted to this 0, this 1 gets shifted to 0, and this remains empty, this box, this flip-flop. So how to fill this flip-flop? So for that, we need to give a feedback to this box actually. So how to give feedback? So what I do is, I just XOR these 2 bits. Let's say first, I just XOR them, these 2 bits, and I fill it out by the XORing of these 2 bits. Okay. So if I XOR them, so 0 plus 0 will give me 0. So this remains empty, so I will fill it up by 0. Okay. Now in the next clocking or the next iteration, what I will do is this bit gets shifted over here. So I will get 1 here, and this 0 gets shifted over here. And this register again remains empty, right? So what will be the value here? It is going to be, so what it's going to be 1 plus 0. So 1 plus 0 is nothing but 1. So this is what it will come here. Similarly, you do the same thing. You shift it again. I will get here 0, and I'll get here 1, and then I will get 1. And again, just do it. Again, I shift, I get here 1, 1, and 1 plus 1 is 1. Again, I shift, I get here 1, 1, and 1 plus 1 is 0. Again, I shift, I get 1, and here I will get 0, and 1 plus 1 is 0. Again, I shift, then I get 0, and this get 1. So it gets repeated after some time. So if you see that, this is what it is. So we started with some initial values in these registers, and that initial values were 1, 0, 0. So that is my shorter keys actually. My there are only 3 bits in the key 1, 0, 0. So this is called initial loading. And with the help of this, and what is happening actually, we have not noticed here. What is happening here is, so first output was 0. So let me write here. So how this sequence looks like. First output was 0. Next output was 1, and then 0, then 1, then 1, then 1. So this is what I will get sequence. And what is the length of this sequence? The length of this sequence is 7. And of course, you keep doing it, it will start repeating. So again, I will get 0. So 0, and again, I will get 1, 0, and so on. So I will get an infinite sequence of bits. But there will be, they will repeat after, 7 bits. So the period of this sequence is going to be, this period of this sequence here is 7, which is, we can write it as 2 to the power 3 minus 1. So this is linear feedback shift register, or maybe in short LFSR of length 3. So I will of course generalize this in more detail. So LFSR of length 3. Okay. So this is what this LFSR. So why it is linear? Because this is a linear function. I'm just XORing these two, this bit and this bit. So I can write it in a more notational form. So if I denote this by S0, this by S1, this bit by S2, then this sequence can be written as, so your S2 is nothing but S3. Your S3 is basically S3 is your S1 plus S0. So you can generalize it. You can write it as Si plus 3 equal to Si plus 1 plus Si, where I is bigger than or equal to 0. So this is the sequence. You have a recursive formula for generating this sequence. And this is linear because you are just, adding so it's called linear feedback shift register. Shift because you are shifting, you are using registers, and you are giving feedback. So the name is quite clear. I mean, it's a very logical name. And of course, it involves deep mathematics, actually. We have not yet gone so far, but of course, we will discuss some mathematics also. But this is how it works. Now, other thing that one should notice here is that I have taken 1, 0, 0. So this is called initial state. So this vector, capital S, I will denote S0, S1, S1. So this is called initial state. Now, if you take a 0, all of them to be 0, then I will get 0 sequence. So usually for cryptography, that is of no use. We cannot use that, as a key stream. If the sequence is all 0, then message goes in plain actually. So it is of no use. So this is called initial state. But if you take any other non-zero initial state, for example, if you take let's say 1, 1, 1, all 3 ones, then what can you say? Whether we will have the sequence of same length or not. So that is what one can see. So here, if you shift it, immediately one can see, if you add this, I will get 0. Again, shift it, 1, 0. If you add them, I will get 0. Again, shift it, 0, 0, 1, and then 0, 1, 0, and then shift it, 1, 0, and what? This 1, 0, and 1. Again, shift it, 0, 1, and 1, and shift it again, 1, 1, 1. We get. So again, after, I just changed the initial state, and still I am getting a sequence of length 7. So here, this output sequence of this LFSR is going to be this sequence. Unlike this, now you see that there are two different sequences, but they will be, shift versions of each other. This is nothing but shifted version of this sequence, and this is going to be infinite sequence. So there are going to be 7. How many non-zero initial states are possible here? Actually 7, because we just remove 0, 0, 0. So there are going to be 7 non-zero initial states. So we are going to get 7 key sequences, and they will be shift of each other actually. And each of, the period of each of these sequences is going to be 7 here. So now this is about, this LFSR. Now let's take another example. So here I'm getting the, period 7. Let's take another example where we don't get full period, actually 7. Of course, what is the full period we have not yet done. Of course, we'll do the mathematical part of it, maybe in the next lecture, or maybe today if time permits. So let's look at another example. So we have these flip-flops, and again, this is how I'm going to generate the sequence. So here, what I'm doing is, I'm just, adding them all, whatever it is. I'm just zeroing it out. Whatever the content of these are. Let's say, again, I take, let's say 1, 0, 0, let's say the same state. And then whatever the addition comes, that I am giving here as a feedback. So this is my, linear feedback shift register, again of order 3. Earlier, I was just zeroing out these first 2 bits, this bit and this bit, S0 and S1. But now I'm zeroing out all the 3 bits. And whatever the outcome is, that I am taking as a feedback. And if I shift it towards right, then my first sequence bit is going to be 0. And if the first sequence, so this is the initial state, let me write it here, 1, 0, 0. And if I shift it, then the next content of this LFSRs are going to be 0. And this 1 will come here. And this remains, backend. So this can be filled up by just addition of all the 3 previous bits. So addition of all of them is going to be 1. Again, I shift it. So if I shift, I get here 1 and 1. And if I add them all, I get 0. Again, I shift, then I get 1, 0. And if I add them, I get 0. Again, I shift, I get 0, 0, and then 1. So I got the, the initial state, 1, 0, 0. That is what we began with. Again, we got this. And, and what is going to be the output sequence? This is going to be the output sequence, basically. 0, 0, 1, 1. And what is the period of this sequence, basically? So here, period is, for this particular, in fact, this generates a cycle. So, this becomes, cycle of length 4, basically. So we get 1 cycle. So I'm just talking about cycle. So we will get 0, 0, 1, 1. This is 1 cycle I get here. Suppose I change my initial state. Again, I take non-zero. Let's take, I take all ones. And then what is going to be the sequence? So 1 plus 1, I shift it, I get 1 here and 1 here. And this addition is again going to be 1. So it gets repeated immediately if I take this initial state. So this is the cycle of length 1 actually. And then you keep on going 1, 1, 1, 1. Your sequence is going to be 1, 1, 1, 1, 1. And it is of no use actually, again. Because if your sequence is all ones, so encryption is nothing but, if your key streams are all ones, then your encryption is nothing but, you have to flip all your bits. So the attacker knows actually, he just have to flip. So this is a very bad sequence to use, in cryptography. And similarly, this sequence is also not very good actually. If you look at, there is a pattern: 0 0, then 1 1, again 0 0, again 1 1. 2 bits are getting flipped and 2 bits are going in plane. So for attacker, you are making the life of the attacker easy. So this sequence is also not good for use. However, on the other hand, the previous example where we have, period 7. So there will we see that the distribution is quite, balanced actually. Number of zeros are same as number of ones. And of course, they will also satisfy various statistical property that a random sequence must have. But nevertheless, so let me come back to here. So this is a cycle of length 1. So we get this cycle 1 1 1. And again, if I take all bits 0, so it turns out that it gets repeated again. So again, cycle of length 0 again 1. Let's take something else. Let's take 1 0 1. This initial state. Then what happens? 0 goes here, 1 goes here, and addition. You just add them all, so you get 0. Again, you shift. Then you get here 1 0. Add them all, you get 1. Again, shift. You get 0 1 and 0. Again, shift it. You get 1 0 1. So this gets repeated. So how many after 4? So this is another cycle of length 4. Length 4. So so here you see that different initial states, they may give you different sequences of different periods. However, in the previous case, you have noticed, irrespective of the initial state, whatever initial state I'm going to choose, the period does not change. So it remains the same. So there must be something, hidden over there. And it must be something mathematically very interesting, that particular example that I gave you earlier. So let me see the time. And so I think I have only 2 minutes. So shall I continue now or maybe in the next lecture?
It's up to you. You can use your 2 minutes or you can stop early, take questions.
Yeah. So maybe I'll use 2 minutes. Okay. So it's a good idea. So, okay. So maybe I'll just define, that will help me in the next lecture. So look at the earlier example. So we had, this is the pictorial view of the LFSR. I will generalize it and of course do some more things. So this was something, we took these 2 bits, the first example I'm taking, and I just dot them out and I get the feedback over here. And this was 0 0 1. This was the first example. So now I can also connect it with the third register like this. And I can, define some multipliers. So since I'm adding these 2, so I take the multipliers C0 here 1, another C1 as 1, and this C2. Because this register I'm not counting at all, I'm not using it in order to compute my feedback. Therefore, I take this multiplier as 0. And this is my initial state S0, S1, and S2. So if you remember my sequence, so I can define this sequence as Si plus 3 equal to C2 times S2, Si plus 2 plus C1 times Si plus 1 plus C0 times Si. So this is it is basically the original sequence, because C2 is 0, C1 is 1, C0 is 1. So I can define in general where these CIs are now coming from, again from the binary field F2. So this is the linear recurrence sequence we can define corresponding to this register, and subsequently we can also associate a polynomial with it. So the polynomial corresponding to this sequence, I can associate something like this. x cube, this is the LFSR of length 3, x cube plus C2 x squared plus C1 x plus C0. So basically this polynomial turns out to be x cube plus x plus 1. Now the question is, maybe yesterday's talk, Samrit has defined what is called order of a polynomial. So here I would like to give exercise that what is the order of this polynomial. So this is going to be a polynomial basically in f2x. So what is the order of this polynomial? Just you try to do this exercise. Similarly, with the next other example also, I can associate a polynomial. So if you look at the previous example here, so here I'm using, okay, where is that? Yeah. So I take this C0 to be 1, C1 to be 1, and C2 is also 1 because I'm using. So the register that we are not using, we can assign multiplier as 0. And the register that are being used in the feedback, we can assign the multiplier to be 1. And this is my S0, S1, S2. So this sequence is basically S3, Si plus 3. Si plus 3 is same as C2 Si plus 2 plus C1 Si plus 1 plus C0 Si, and I is bigger than or equal to 0. So you can you can generate an infinite sequence of zeros and 1, and corresponding to this, because of these Ci's, you can define a polynomial. So that polynomial I can define like fx equal to x cube plus C2 x squared plus C1 x plus C0. So which is going to be x cube plus x squared plus x plus 1. Again, this is a polynomial over f2. You can also compute its order. What is the order of this polynomial? So, so basically, essentially, this sequence is completely determined by just knowing what are your CIs. So if you know your CIs, you actually know what is your LFSR. So, or if you know the polynomial. I think I'll stop here. And I'll continue with the same topic in the next lecture, that is on Thursday. Thank you very much.
Yeah. Thank you very much, Sartaj, for your lucid talk. I think there are some questions I see in the chat box. So I don't know if the audience want to say it themselves. So, for example, I see Shruti Pradeep wants to know whether you will give any application of one-time pad cipher. No, I am not going to give any application of this. Okay. And Hitesh Kumar Patak wants to know, is there any restriction on the length of key stream generator? Length of key stream generator. So, of course, we want the period as large as possible. So, if you take LFSR of only length 3, the period is going to be 7. So of course cryptographically it is of no use, and of course we do not use LFSR as such. In the design of a stream cipher, just one plain single LFSR, because you can break it by yourself. If you have a LFSR of length n, and if somehow you know the 2n bits of the key stream, then it's a matter of just solving a system of linear equation. You can immediately break, and you can, build your own LFSR that generate the same key stream, and you can break the cipher. So therefore, in practical scenarios, the period has to be as large as possible. Also, they use the combination of LFSR. So as I was telling you, I must give you, the picture of, so this is the picture that is being used in, GSM cipher, GSM network. So A51. So you see that there are 3 LFSR that are being used here. One is of length 19. I think, this LFSR is of length 19. This is of 22. This is of length 23. So 3 LFSR of different lengths have been used. And, the clocking is being done based on the majority rule. What is the bit over here? This is at the 8th position. This is at the 10th position and 10th position. So, one has to look at what are the bits in these positions. And the majority bits, suppose here 0, here 1 and 1. Then this LFSR will be clocked, this will be clocked, this will not be clocked.
And similarly, if there is one here and 0 here, then this will be clocked, this will be clocked, and so on. So it's in practical scenario, it is not only one LFSR that is being used. It is the combination of LFSR with several nonlinear functions. There are various kind of models for designing stream cipher. We have Jeffs generator, we have combiners, we have nonlinear feedback shift registers where the feedback is not computed linearly. It is being computed by a nonlinear function. So those things have to be, it should be combination of, linear feedback shift register and maybe some nonlinear functions in order to increase the complexity. And for linear feedback shift register in order to have large period basically. So the combination has to be used. So I don't know whether I have answered the question or not.
Because that is for Ritesh to say.
Okay.
We will not. He's welcome to speak, but I see that Vikas Kumar has a question, and he says, if the induced probability distribution on ciphertext space is uniform, then what can we say about the secrecy of cipher?
Oh, so if the that is uniform, here we are proving that the distribution of cipher bits, that is actually uniform, and that helps us to prove the what is called perfect secrecy. So the question is, I think I don't know what is the exact question. Maybe you can you repeat it again?
Sure. It says, if the induced probability distribution on ciphertext space is uniform, then what can we say about the secrecy of cipher?
Induced, I don't understand what he means by induced. Maybe if he is there, maybe he can.
Yeah, because
induced, I mean that because we have a probability distribution coming from the plain text and the key space on the ciphertext space. No?
Yeah.
For each Y in ciphertext space.
So so Ritesh is saying that he is satisfied with the answer.
Yeah.
Now I can, yeah. Okay. So what I told you in the one-time part, what is happening is we don't know what is the distribution of the plain text bits. But if you are using a truly random sequence of bits for as your key stream, then what happens is the distribution of ciphertext bit is also uniform. So that is what I told actually, and in fact one can prove that. But I don't understand what you mean by induced. Maybe the question is not clear, or maybe I'm not able to answer your question.
Okay, maybe we can let Vikas and Sartaj talk to each other later. There is one more question, I think, let's say, by Vatsal Jha. What are the possible attacks on the LSR crypto system?
There are many, attack. Cube attack is there, algebraic attack is there. There are fast algebraic attacks, correlation attacks. Many attacks are there.
Mm-hmm.
So several attacks are there actually in the literature. So this talk was primarily, I just wanted to motivate some young student who are perhaps not aware of this subject. That was the primary motivation. So I have not gone into too much detail of every aspect. It is only the at very, very elementary level.
And Ajay wants to know if you can recommend some good book to start with for cryptography and algebraic concepts.
So for sequences, I would say there is a very nice book by Solomon Golub, and the title of that book is Shift Register Sequences. And there is another book by Solomon Golub and Guang Gong from University of Waterloo. So the title of the book is not very clear to me, but it is, the title is not known to me, exact title, but that deals with the sequences only. Two books that completely deal with the sequences. And there you will find, it's a very mathematical detail of each of these actually. It's a very mathematically, interesting subject, very interesting area. And the idea is basically how to design secure key stream generator by combining LFSRs with some other nonlinear functions. Okay.
All right. I think, okay, so I think Gannon wants you to write the names of the book here. I would imagine that if you Google on Solomon Golem, you will probably get some information. But Prasad, you can. You want to mention those books in the chat?
So there is a book by Solomon Golem. The title is Shift Register Sequences. It's published by Aegean Press, if I'm not wrong. And other book is by Solomon Golem and Goang Gong. So if you Google it by author name, you will get it. And some basic, of course, every cryptography book has got at least one chapter or maybe half chapter devoted to only stream ciphers. So, for example, extension talks about stream ciphers in the very first chapter itself. And similarly, the book I was referring to, Christopher Parr's book, so that also talks about stream ciphers in their second chapter. So every cryptography book will have a little bit of, but if you really want to understand the sequences in general over any arbitrary finite field, then perhaps this Solomon Golem and Goang Gong's book is very good. And there is one chapter about sequences in Niederreiter, Liddell and Niederreiter's book on finite fields. So that's also very rigorous treatment of sequences given over there.
Okay. I guess other than, okay, there is one more question. If the registers generate a repeating sequence, can we generate a repeating block a priori and not use registers overall?
Block, I don't know how to generate blocks. It's okay. Okay, so that is what, so basically, so far I have been treating, just elements coming from the field F2. So only 0 and 1. So instead of F2, if you restrict your elements in F2 to the power m, a field of size 2 to the power m. So instead of just one bit, you will have, vector of length m in each register. So yes, you can generate a block of length m in one iteration. So you can say m could be your 32-bit, for example. So you can generate 32-bit or 64-bit in one iteration. So it is possible. So that's basically, you have to define the linear feedback shift register over an arbitrary field, and that is what I'm going to do in my next talk. And this is basically the two of my lectures. They are basically, I'm making background for last lecture by Dr. Samrit Ram, who would be talking about this not only bits, you can take words actually. So he'll talk about splitting spaces and sigma LFSR, things like that. So these two lectures are going to be useful in order to follow the talk by Dr. Samrit Ram.
Okay. So thank you. Thank you very much, Sataj.
Thank you, sir.
Thank you. I guess we have a break now of about 17 minutes. And the next lecture will be at 3:30 by Alberto Ravenani. Alberto, you are there, I think, already.
Yes, I'm here. Can you hear me?
Yes, I can hear you, Alberto. So anyway, you can, hi.
Hi.
Virtually.
Hi.
Hello.
Okay. So we are meeting after 15 minutes then.
Yeah.
Okay.
So, you want to try your tablet and laptop or your...
Yes, so I see that...
Later,
oh, okay.
You get a cup of coffee.
Yes, so now I can present myself. So let's see. So I should be able to share just the Adobe window. Yeah. I'm sharing now, let's see. There it is. And then I guess you would like me to remove this.
Oh, yeah, you can keep it. Yeah, okay, fine. Maybe remove that.
Okay, so that should be it, I think.
All right, that looks simple enough. So.
Yeah, so I have two laptops. I find it a little bit annoying in Google Meet that you can only see essentially your screen and you cannot see the faces of people or the. So there are actually two me in the list of participants.
We have. So you're in Eindhoven or in Italy?
No, I am in the Netherlands now, in Eindhoven, at home.
Okay. Yeah, so am I.
Yeah.
So, yeah, if you don't mind, I'll just grab some tea or
Of
something.
course. Yeah. We meet here in like 10 minutes or so.
So, yeah.
Good. Yeah, excellent.
So, see you.
Bye-bye. See you.
Okay.
Good afternoon, sir.
Good afternoon, Arun. We have 2 minutes by my watch. So then I'll just say a few words in the beginning, and then it's all yours, Alberto. So it is still morning for you, isn't it?
Yeah, it's 11.
Yeah, okay. So good morning.
It's 11 in the morning. Oh, I should do full screen.
Okay, so I think it's time. So it's my pleasure to introduce our next speaker, which is Professor Alberto Pavanani, currently at the Eindhoven University of Technology, or TUE, as it's popularly known. Alberto is a very prolific researcher, and recently I became somewhat interested in the rank metric code and was trying to understand it a little bit, and I came across his papers, and I was always very impressed by the quality and clarity of his writing. So when I thought I should have some lectures on the rank metric code, I decided to invite him, and thankfully he agreed to lecture in spite of a busy schedule. For those of you who know Alberto, comes from Italy. Actually, I just noticed from the town of Romeo and Juliet. And he did his PhD in Switzerland, in Neuchâtel, with Elisa Gorla, and has had a postdoctoral stint in Toronto and also in Dublin, where he was a Marie Curie Fellow. And now he has a regular position as an assistant professor at Eindhoven in the Netherlands. And he will speak to us, in fact, give 3 lectures on network coding and the rank metric. Alberto, please.
Yeah, so thanks a lot for this generous introduction. I would say, yes, so this is the first of 3 lectures on rank metric codes. And since I have 3 lectures, I decided to devote the very first lecture to the motivations. Okay, so hopefully in this presentation, I'm going to answer the question, why rank metric codes? So what are the applications of rank metric codes? What is the motivation behind using the rank metric in digital communication? And one of the reasons why I decided to do this is because while rank metric codes are nowadays quite well covered in the literature, in coding theory, there are still not many references explaining how the rank metric naturally shows up in the context of digital communication and network coding more specifically. And then I thought maybe a graduate school is the good place where to essentially inflict this on people. So this motivates the choice for a first lecture for the motivations of rank metric codes. Okay, so let's get started. So not many proofs in this lecture. Proofs will come in lectures 2 and 3. Okay, so the outline of a presentation is just 2 slides, and main presentation is 2 parts. Main presentation is part 1, where I will tell you what network coding is about and how the rank metric naturally shows up in there. And then we will see the statement of a very nice theorem in section 1. And although I don't have the time to prove it entirely, I will point you to a reference, including the proof. I would like to comment a little bit on the proof strategy. Okay, that's part 2 of my talk. Okay, so let's get started with network coding. So network coding, it's a relatively new topic in information theory, was born around 2000, and it's about data transmission over networks which are possibly noisy, okay, or lossy even. So, and of course, you can think of many applications of this. I don't even need to mention them, but streaming, for example, is one. And then patches distribution, also peer-to-peer networking, and so on. Okay, so the typical situation that we study in network coding can be depicted in just one figure. So here you see a source of information, S, okay, attempted to transmit n vectors, v1 through vn. These are vectors with entries from a finite field fq, and they all have the same length, m. And the source attempts to transmit all these vectors to a bunch of terminals, t1 through t capital M. Okay, and so the problem specifications here are that, well, the vectors, as I said, they belong to the finite field of q and then to the power m, and then the terminals demand all the messages. Okay, that's very important. So this is called multicast. So as I said, this is very important because if you start imposing demands, like for example, terminal 1 only wants a subset of the messages, the problem becomes completely different. Okay, and actually much more challenging. So we focus on the multicast situation. All terminals want to receive all the messages. Okay, well, the question is, of course, what should the intermediate nodes do? Because we know what the source wants to do, deliver all the messages. We know what the terminals want, receiving all of them. Okay, but then what about the intermediate nodes? Well, then we have to keep in mind what our goal is, which is to maximize the number of messages that are transmitted to all terminals, as I said before, per channel use. And that's a very informal definition of rate, information rate, which is not formal. It can be made formal, but it's good enough for us. Okay, so for us, the rate of the communication is the largest number of messages that the source can transmit to all terminals. Oh, I forgot to say, if you have any questions, please just free to unmute yourself and ask. I will try to keep an eye on the chat, although I'm not super good at that, but I will try, okay? But just feel free to unmute yourself, and ask things. Okay, so that's what our goal is. And, well, a traditional solution to this problem, transmitting messages through a network would be routing, and I will tell you in a second what it is about. But then network coding originated from a very nice idea from 2000 by Schwede, Kai-Ling, and Young, which is about allowing the intermediate node to recombine information before forwarding it. Okay, that's the key idea in network coding, and one of the most efficient way of illustrating this is via an example. So this is a so-called butterfly network. That funny reason why this is the name, but if you remove those two edges, what is left looks like a butterfly. That's really why it's called like that. Yes, so let's say that source S wants to transmit messages V1 and V2 to two terminals, T1 and T2. Okay, so not a lot of room for creativity in the beginning. Let's say vector V1 and vector V2 over the outgoing edges. And then there you have these two intermediate nodes, and the most sensible thing to do there is to just forward the information. Now here comes the interesting part. Okay, now this node V receives two vectors, V1 and V2, but only has one outgoing edge. So the traditional approach to communicating over networks would be to use routing. And in that scenario, the vector would pick one of the two vectors, V1 and V2, and only forward that. Okay? But in network coding, and that's the simple but very nice idea by Schwede, Kai-Ling, and Young, is that a node V, which is in a bottleneck position, so to say, instead of picking one of the two messages and forwarding just that, could decide to forward a superposition of the two messages. So V1 plus V2. So we said that vectors, well, they are really vectors from a vector space, so the sum is well defined. This works over any group in principle, but we keep it simple to vector spaces. And then, so instead of picking one of the two messages and forwarding just that, the node forwards a superposition of the two messages, which is the sum in this case. And then the terminal node here just forward the sum. Okay, and this strategy is better than routing. And well, if you look at the scheme, terminal 1 receives V1 and V1 plus V2, and terminal 2 receives V2 and V1 plus V2, so it's just enough to subtract one of the two received vectors to the other one to be able to recover both messages, right? Both V1 and V2 just performing elementary linear operations on the received inputs. Okay, and it can be proved, as I said, this strategy is strictly better than routing, meaning that it's not possible, no matter what routing strategy you use, to deliver 2 messages per channel use, not even in average. Okay, so even allowing multiple uses of the channel with routing, you certainly cannot beat, and actually you can never achieve 2 messages per channel use. Okay, so I hope this part is clear and this example is clear enough to understand what's going on. And I want you to have the formal definition of network that we need in network coding. So this is actually a definition where, together with Frank Shishan, we isolated all the really key ingredients that you need for a well-behaved theory of network coding. So we wrote a paper about this, and so if you remove, it turns out that if you remove any of the assumptions that I have in this definition, there is one major theorem in the theory that fails. Okay, so this is kind of a minimal set of assumptions for a network to function in the theory. So a single source network for me is a 4-tuple calligraphic N, V, E, S, and T. Now VE is a finite, directed, acyclic multigraph. So I hope you all know what this is about. And then S is a very special vertex called the source. And then T is a subset of vertices, and it's a set of terminals or sinks. And then, well, I said multigraph, so we allow multiple parallel directed edges. Okay, we will see an example later. And we also assume we have a series of assumptions that, as I said before, they guarantee that the theory works smoothly. So we have at least one terminal, and the source is not a terminal. And then any terminal is connected to the source by some path in the network. This source is a source, meaning that does not have any incoming edges, and the terminals do not have any outgoing edges. And then it's very important, for every vertex V, there exists a direct path from the source to V and from V to some terminal. Okay, so this means that there is no isolated vertex in the network. Okay, and then a little bit of terminology here. So the elements of V are called the nodes of the network, and the elements that are not sources, well, not the source and not terminals, are the intermediate nodes of the network. And then a little bit of notation I'm going to need later. In V is the set of incoming edges to a certain node V, and out V is the set of outgoing edges for vertex V. Okay, so remember our question, how many messages, what is the largest number of messages we can transmit over a network from the source to all terminals? So the first thing you try to do when you have such a question is to get a bound for this number. Okay, and that's what the min-cut bound does. So I'm going to state the theorem, okay, and then I'm going to discuss achievability, which is essentially the remainder of the talk. So N is my network, S is the source of the network, and T is the collection of terminals. So now this theorem by Schwede, Kai, Lee, and Yang, also from 2000, says that the multicast rate of any communication over the network, so as rate, so that this largest number of messages we can transmit, upper bounded by a graph theory invariant of the network, which I denote by mu. That's the mu of N, which is the minimum of the min cuts between the source and the terminals. So the min cut between two vertices in a directed, like in a diagraph, is the minimum number of edges that you have to remove in the graph in order to disconnect S from Ti. So the min cut from S and Ti. Okay, so in order to compute this quantity, mu, which is an upper bound for the rate, you have to go through all the possible pairs, all the pairs S and terminal, and compute what the min cut is. Okay, and then you get a series of numbers, one per terminal, and then you take the minimum of them. That's the mu of the network. Okay, and the theorem says that this is an upper bound for the rate. Okay, so we will see how to compute this in an example shortly, but then whenever you have a bound, the question is, of course, can I achieve this bound? Okay, so the question now becomes, can we design node operations, which we're going to call network code, so that this bound is achieved? And the main theorem of network coding says that the answer to this question is yes, provided the finite field is large enough. Okay, and in fact, not only that, but we can achieve this bound just using linear operations on the intermediate nodes. Okay, so that's the main theorem in network coding. So let's see an example. So I already showed this, the butterfly network, where we had the source, this bottleneck node, and then we were using this strategy to deliver 2 messages per channel used to both terminals. And the key, if you remember, was to forward a superposition of the vectors, the sum v1 plus v2, which I have in red in my picture. Okay, so let's compute the bound in this example. So the min cut between S and T1, okay, S and T1 is the minimum number of edges I need to remove from the network in order to disconnect them. Okay, and then it's easy to see that this number is 2. Okay, if you remove only 1, you're not going to be able to disconnect S from T1. And the same by symmetry applies to T2. Okay, so that the min cut between S and T1 is the same as the min cut between S and T2. They're both 2, and therefore the mu of the network is precisely 2. And then this strategy actually delivers, if you think about that, precisely 2 messages per channel use, right? And therefore it's optimal. Okay, and we actually achieve this with just linear operations on the received and transmitted vectors, right? Course linear, and then transmitting the sum, which is also linear. Okay? Yeah, so as I said before, the main theorem of network coding says that this is always possible. Okay, so no matter what the network is, this is always possible provided the base field is large enough. Okay, and that's the so-called max flow min cut theorem, which, careful here, this is not the max flow min cut theorem from graph theory you might see in algorithm courses. That's a different thing. And so here's how it works. So I have a network N, and I call N the mu of that, which we now know how to compute. Remember, the minimum of the min cuts. And then assume that the source sends messages v1 through vn. These are vectors. Okay, so there is a typo here, sorry, that's fq to the m. Vectors, n vectors of length m with entries from fq. And then assume that the nodes perform linear operations on the inputs they receive. So they're using linear network coding, just in the example we have seen. Okay, but possibly not just the sum, okay, more sophisticated, possibly linear combinations on the inputs. And then terminal T is gonna collect vectors from the incoming edges. Okay, and it's gonna collect R of T of them, the number of incoming edges, and I denote these vectors W1T, W2T, up to WRT T. Okay. So now, since I'm using linear operations inside the network, each of the received vectors, Wi, okay, can be expressed as a linear combination of the originally transmitted vectors, right? Just because every node, every intermediate node is just recombining linearly the messages, okay? And if every node does that, what I'm gonna receive to a certain terminal is gonna be a linear combination of the original vectors V1 through Vn. So each Wi is a linear combination of the Vj's. And therefore, I can write this matrix equation, so I can put all my W vectors in as the rows of a matrix, all my V's vectors also as the rows of a matrix, and then I have that the matrix of the W's is equal to the matrix of the V's, and then multiplied by a matrix G, okay, which depends on the terminal, okay, and multiplication is from the left. Okay, so I have this nice matrix equation, and then GT, which has size RT by N. As I said before, it depends on T and is called a transfer matrix at terminal T. And this matrix takes into account all the linear combinations that were performed by the intermediate nodes of the network. So now the Max-Flow main-cut theorem, which was proved originally in 2002 and then with a very elegant argument that I will try to sketch by Kötter and Medard in 2003, says the following. Well, first of all, it's a very important piece of the theorem. Without loss of generality, R of t, so the number of incoming edges to terminal t, is equal to n, which is precisely the mu of the network, and that's the same for every terminal. Okay, so first part of the theorem says that without loss of generality, we can assume that each terminal has exactly the same number of ingoing edges, and that number is precisely n, the mu of the network. And then second part of the theorem says that if Q, so the size of the base field, is at least the size of the number of terminals, the size of the set of terminals, then there exist linear node operations, okay, so a choice of linear operations for the intermediate nodes, such that the matrix G of t, is n by n, that's guaranteed by part 1 of the theorem, but it's also invertible, and that's true for all terminals at the same time. Okay, so if you don't understand what the statement of the theorem is about, so please tell me now, because this is important and we're going to need this later. Okay, so I have a picture to describe the theorem. Okay, so here I have my source and the vectors I want to send. I organize them as the rows of a matrix, which is then of size n by m, entries over fq. And then I have a terminal there, and terminal there is receiving g of t by the vectors of all the v's. Okay, and then I know from the theorem that g of t is n by n and invertible for every terminal, and I'm using that q is large enough for that, at least the number of terminals itself. Okay, but then the coding is extremely easy, right? Because, the terminal, the matrix G of t is known by everybody. It can be decided at the very beginning of the transmission. And then recovering the V's is extremely easy because it's just enough to multiply what you receive by the inverse of G of t. Okay, so decoding is just multiplication by the inverse of G of t. Remember, G of t is n by n and invertible. Okay, so that this all makes sense. Okay, and in this way, every terminal is able to recover the messages, the VIs. Okay, so the G of t, remember, is different for every terminal, but that's not important. So each terminal is going to invert its own G. Okay, so let's verify the theorem in the example that I had before. Source, terminals, that's the butterfly network, and the sum, on which I commented before. Now you see that terminal T1 receives which linear combination of V1 and V2? Well, V1 over the first edge, and then V1 plus V2 over the second edge, and therefore I can describe what terminal 1 sees as this matrix multiplication. Okay, and then you see this matrix is invertible. Okay, and then it's enough to multiply by its inverse to recover V1 and V2. And the G of t for terminal 2, GT2, is also invertible. Okay, and this actually works over any field. Okay, so these two matrices are invertible over F2, but over any other field you may like. Okay, so to summarize, we have this mean cut bound, which says that the multicast rate of any communication over the network satisfies rate upper bounded by this graph theory invariant of the network, the min cut, the minimum of the min cuts between source and terminals. And then the max flow min cut theorem tells you that if Q is sufficiently large, and we have an explicit bound for this, then this rate is achievable in one shot, so using the network just once, and with linear network coding. Okay, so this is very nice because we have a bound and we also have an achievability result. So the bound can actually be achieved if the base field is large enough. Okay, so very elegant. And then the problem of what is the smallest field, for which there is a solution, well, that's still open. So there are various conjectures about this. I think the most popular is that you require the size of the field to be roughly the square root of the number of terminals, but nobody really knows. Okay, so that's an open problem in network coding. What is the smallest queue, the smallest field size over which there is a solution to the network coding problem? That's open. Okay, so I would like to move to error correction and then start talking about the rank metric now. So if you have any questions about network coding more generally or on the part we have seen so far, please ask them now so that I also know if I'm losing you or not. So let me see the chat.
See in the chat, so I think.
Oh, sorry. Yeah, I said I'm very bad with the chat. Okay.
It will happen to me too. So
if the register generates a repeating sequence, can we use? No, this I think is not for me.
The previous lecture. Yeah.
Okay. No, there is no question then. Okay. Good.
Hello, sir. Sir.
Maybe there is a question.
Oh, okay. Yeah.
Yes, sir. In the first or second slide, you told that AC is not a subset of T. I mean, AC is the source and T is a terminal. So you told AC is not a subset of T. Does that mean that any source can be terminal, or neither of source that is not terminal?
No source. Like the source, like I concentrate on the single source scenario here. So there is only one source for me, and the source cannot be a terminal.
Okay, it's a single source. Okay.
It's single source, and
it can be
the
terminal.
source. No. The source is not a terminal. Yeah.
Okay. Thank you, sir. Thank you.
No worries. Okay, so let's move on and talk about the rank metric. Okay, and so the context in which the rank metric was essentially proposed for applications is an adversarial context. Okay, so which I'm trying to sketch now. So the model we focus on is the following. Okay, and that's very important for the theory because it can generate confusion when talking with information theorists. So the model is this. So there is one adversary that can change the value of up to T edges, okay, of the network. Okay, and T is called the adversarial strength. Okay, and then the adversary knows, that's the second assumption in the model, knows the network code. So the operations performed by the intermediate nodes of the network. And you can think of those as pre-assigned. Whether they're linear or not is not important, because that's the model we concentrate on. Okay, so there is one adversary acting on the network. Okay, there is no probability of errors happening. Okay, that's the context in which the rank metric was proposed first. So, and I would like to explain with a picture what the main problem is here. Okay, so let's take this slightly more complicated network than the butterfly one. Okay, I still have one source and two terminals, but then I have more intermediate nodes that are connected as in the picture. Okay, so now suppose that the adversary manages to corrupt the value. Okay, remember over the edges vectors are traveling. Okay, and then the model says that the adversary is able to change the value over one of the edges. So say that the adversary manages to change the value of this edge. Okay, so now we said that the intermediate nodes are recombining the vectors linearly. Okay, so now this intermediate node is using both the values of these edges to compute the value of the outgoing edges, right? Because I'm performing linear combinations and then I'm sending the results, essentially. So this means that since I am recombining a potentially corrupted vector, I get two potentially corrupted vectors, right? Because they're both affected by the computation, which has the corrupted vector, as input, right? So now the same applies to this other intermediate node, which computes the value of 4 outgoing edges based on the value of one potentially corrupted edge, right? Generating in this way 4 more potentially corrupted edges. So you see, this looks extremely bad because the adversary managed to corrupt just one vector, so touching only one edge, but then I end up with 5 terminal edges potentially corrupted with a wrong value on, essentially, right? So that's a very well-known phenomenon in network information theory, and it's called error amplification. Okay, so we start from just one tiny possibly error there, and then it propagates. Not only it propagates, but it also gets larger, right? And this is, if you think about it, this is really intrinsic to this recombining and computing things inside the network. If you had just forwarding, okay, so the traditional solution, which was routing, so just picking vectors and then forwarding them, okay, so what was wrong stays wrong, and what was correct stays correct. Okay, so this is really intrinsic to the idea of recombining the messages before sending them. Okay, but on the other hand, we really like network coding because we have just seen that it fixes, right, the problem of achieving the largest possible rate over a network. So on the one hand, network coding seems like very good because it gives us a better rate than routing. On the other hand, it has this problem of error amplification. And that's precisely where the rank metric kicks in. Okay, so the original solution that people tried for a few years to this problem was to design the node operations more carefully. So for example, you can think of fixing the errors within the network before sending, okay, or using more sophisticated versions of routing, essentially. But then there is a better solution, which turns out to be based on rank metric codes, okay, which was proposed around 2008, and that's what I'm gonna describe in the next few slides. Okay, so suppose that we use linear network coding. Okay, so we combine the messages linearly at the intermediate nodes, and then n is the mu of my network, just as before. Again, the source transmits vectors v1, vn, which we organize as the rows of a matrix, which I call X. Okay, and there I have a terminal, and the terminal receives g of t by X. And by the max flow min cut theorem, g of t can be made n by n and invertible for all terminals if the size field is large enough. Okay, so that's what we have seen already. So now let's see how to handle the errors. Well, in an error-free context, X is sent, so the matrix X is sent. So I talk about the matrix being sent, okay, but of course I mean the rows of the matrix, so the vectors are sent. Okay, and then what is received is g of t by X, and that's received by terminal t. That's, you know, if everything goes okay. No adversary acting, okay, but then if error occurs, the matrix X is sent, and then what you receive is a matrix Y, Y of t, so this depends on the terminal, which is not g of t by X, of course. Okay, and then the key observation that motivates the use of the rank metric in network coding is this one, so this theorem by Silva, Kötter, and Shishan from 2008. So they observed that if at most the edges are corrupted in the network, okay, then you take the matrix that was received, Y, and then you subtract G by X. So this is the matrix that was received, and this is the matrix that should have been received. Okay, so you take these two matrices, they have exactly the same size, you compute the difference between them, and then you compute the rank. So this theorem tells you that if at most the edges were corrupted, then the value of this rank is no more than t. Okay, so the number of edges that can possibly be corrupted, which we described as the adversarial strength before, okay, is an upper bound for that's what is called the rank distance between the matrix that should have been received and the matrix that was actually received. Okay, so and this result is where they got the idea of using the rank metric as a measure for the discrepancy between the matrix that was received and the matrix that should have been received. Okay, and that's the definition then of rank distance between the two matrices A and B as the rank of their difference. So I really like this result because it essentially proposes a change of perspective. Okay, so if you look back at the picture that we had before, right, where just one error here propagated and amplified and gave us 5 corrupted terminal edges, well, the result by Silva, Kötter, and Shishon tells you that you're kind of looking at this picture in the wrong way. So the number of corrupted edges, so the number of edges with the wrong value is not the right measure you want to use for how wrong things went. Okay, so if you use the rank metric instead, so this result is telling you that errors still propagate, but they don't amplify anymore. So you don't have this very unpleasant situation where essentially you have one error before and then 5 errors. Okay, so if you had 1 error, you still have 1 error, like in the worst possible scenario. Okay, so is this clear? Okay, so this is like an idea to measure things in the right way, so to say. Okay, very good. And that's what introduced and originated all this interest in the rank metric. So remember, the rank distance between two matrices is the rank of their difference. Okay, so now let's see how the scheme works. Again, my source, my matrix of size n by m, and then the terminal receiving g of t by x. X is sent. What should have been received was g of t by x, and that was what received was y of t. And then, as I said before, the result by Silva, Kötter, and Shishon tells you that the adversarial strength t is an upper bound for the rank distance between y and g by x, which is not particularly important for us and for this talk, but it's very important for decoding, so I want to have it in my presentation. This is also the rank distance between the inverse of g by y and then x. Okay, that's very important for decoding. And then I have this observation, which I already mentioned. According to the rank metric, errors still propagate, so you cannot fix that, okay, but they do not amplify anymore. Whereas if your metric was number of wrong vectors somehow, well, then you really have the problem of amplification of the errors. In the rank metric, you don't have this anymore. Okay, so this also motivates the definition of rank metric code as an FQ linear subspace of FQ n by m, sorry. And these objects are the topic of the next two lectures. So for the next couple of days. So the next two lectures are about the mathematics of these objects. Okay, so that's the definition, which you need to remember. So rank metric code is an FQ linear subspace of the matrix space FQ n by m, sorry. And then an important parameter, which just as in codes for the Hamming metric measures the correction capability of the code, is the minimum rank distance of the code, which is the minimum rank of a non-zero matrix in the code. Just like in the Hamming metric, the elements of the code are called code words. But unlike in the Hamming metric, they are now matrices, all of the same size, n by m. Okay, so schemes based on rank metric codes are very, very interesting because of 3 main features they have. So first of all, they are capacity achieving. So I don't have the time to explain what this means in this context, because I would need to introduce the notion of capacity region, and then, yeah, it's the machinery for describing these results in an accurate way is a little bit heavy, so I decided to skip this. But this just means that there is a bound, for the number of messages that can be retrieved by all terminals, assuming an adversary acting with a certain strength, so capability of corrupting things. And then using rank metric code, you can actually achieve that bound over sufficiently large fields. Okay, this is what capacity achieving means. The second feature is that they are compatible with linear network coding. So this is very nice, meaning that we can use the strategy of recombining the vectors inside the network, which is precisely where we started from, okay? And you can combine this with using the rank metric. And those two things play nicely with each other and gives you a capacity-achieving communication scheme, okay? So remember, using the rank metric was actually motivated by this recombining things inside the network, okay? So that's kind of what we expected and the problem we wanted to solve in the very beginning. So that's no surprise, but still very interesting and nice. We kind of achieved what we wanted to do. And then 3, extremely important, separability. So you can actually design the network code, so the way of scrambling things inside the network, and the rank metric code independently from each other. Okay, so this means that you have a network and you already found a very nice solution for solving the network coding problem. And now somebody comes and say, well, actually, there is an adversary who could potentially corrupt one edge from your network. And then you go like, okay, so keep your network code that you computed already, and now you add this rank metric code on top of it. Okay, so that's separability. And of course, it's very handy in scheme design. And then, so property tree is very important, but unfortunately, as soon as you leave this very simplified scenario that I told you about, one adversary acting on, well, with a certain, like acting on any edge of the network with the restrictions, of course, on the number of edges that can be corrupted, well, you don't have this separability property anymore if you consider slightly more general scenario, okay? So for example, something we studied with Frank are erasure adversaries or restricted adversaries, so adversaries able to corrupt edges only from a certain vulnerable region of the network. Well, if you start to make the scenario a little bit more sophisticated than the plain one we described so far, unfortunately, we can provably show that you cannot have compatibility with linear network coding and separability at the same time. Okay, but for the simple scenario I described before, we do have that. I just wanted to, so in this lecture, I also try to tell you a little bit about the open problems or about what goes wrong in case you are interested in the problem and you want to investigate a little bit more on yourself, by yourself, sorry. Okay, and there is a reference for this, okay? And then another thing that I would like to stress, which is very important, I already said that before, the noise in all these models where rank metric codes are used is adversarial in nature, okay? So if you start using probabilistic models, well, you need different methods, more from classical information theory, and I have a table summarizing a little bit the differences between what's called probabilistic or classical information theory a la Shannon, if you want, and then zero-error information theory, which is also a la Shannon, but from a different paper, the zero-error capacity of a noisy channel, which is much more discrete in flavor. Okay, so I have a few examples or description, if you want, of this two kind of souls of information theory. In the probabilistic approach, the noise follows a probabilistic distribution. Probably you know the binary symmetric channel, and in the zero error world, instead the noise can be thought of as an adversarial noise. So in the probabilistic setting, we allow small probability of decoding failure. So for example, the message can be repeated. But in the zero error world, probability just doesn't make sense. Okay, so if you think of an adversary, well, the adversary does not, since we call it an adversary, the adversary does not obey any probability rule, in performing the attack. The adversary always does the best it can to screw up things. Okay, so there is no notion of probability attached to this context. They, of course, have different applications precisely because of the different model. So probabilistic information theory works extremely well for satellites, phone, space missions, trains, well, compact disk and DVDs and all of that, flash memories. Zero error information theory instead more works for, well, adversarial scenarios like Byzantine attacks or storage, okay? And then if you, like, the capacity and the performance of error correcting codes can be very different based on in which word you look at them. So for example, block codes with the Hamming metric, many of you are familiar with these codes. They're not capacity achieving if you look at them from a probabilistic information theory point of view, but they are capacity achieving from a zero error information theory point of view over sufficiently large alphabets. So the solution here is MDS codes. So rank metric codes sit here in the zero error information theory column. Okay, and then if you are interested in the probabilistic network information theory, that's still a case-by-case theory and still a very open problem in information theory. Okay, so any questions about this? Okay, I just try to make clear what the distinctions are and what the model is about and what is the context in which we apply rank metric codes. Yes?
There seems to be one question from Preeti. Rank metrics also defines strength of adversary.
No, these are two different things. Okay, so basically, a key parameter, let's see if I, yes, okay. So basically, if you want to protect the network or the communication from an adversary with a certain strength T, you're going to need a code with like large minimum distance with respect to T. Okay, so that's the link between the minimum distance of the code and the adversarial strength. Okay, just like in the Hamming metric, if two components of the vector can be corrupted, you want a code with minimum distance larger, like a 5 or something like that. Okay, so yeah, but the ranks, of course, oscillate within the code, so they're not all of the same rank. So I don't know if this answered the question. So a rank metric code is a collection of matrices. Okay, it's not just one matrix. Okay. Okay, good. Very good. Okay, so I would like to conclude the presentation with a few comments about the Maxlow mean-cut theorem that I mentioned before. So as I said, this is a very important theorem. It's kind of the main theorem in network coding. And, well, that's the statement, which I recall in these slides. And the network, little n is the mu of the network. Then we have our assumptions that the source sends messages v1, vn. The same typo here, fq to the m, okay? And then the nodes perform linear operations on the received inputs, and then terminal t collects vectors wj's from the incoming edges, and then you can write the wj's as linear combinations of the vi's. And each matrix, that's what the theorem says, each matrix, each transfer matrix can be made of size n by n, so square and invertible at the same time. Okay, so as I said before, so giving the full proof requires a little bit of time, okay, and especially if you want to do it like in a rigorous way. So I actually teach this proof in the coding theory course. I offer a TUE, so this year the lecture notes are publicly available. So in case you really want to see all the details of the proof, well, the notes are freely available, so you can actually have a look in there. So I'm not proving the theorem entirely. So what I would like to do is to comment a little bit on the two main ideas that are used inside the proof, okay? Because I think it's a very elegant argument, and it's based on two branches of mathematics, which are combinatorics, graph theory, and algebra. And there are two key results from these two theories that are combined in a very elegant way within the proof, and I would like to comment a little bit on that. So the first theorem we use in the proof, it's Menger's theorem from graph theory / combinatorics, depending on your view on things, okay? And so Menger's theorem says the following. So suppose that V is a directed acyclic multigraph, just like a network, okay? And then S and T B vertices, okay? So these are vertices, okay? Then the mean cut between S and T, this magic quantity we kept computing, for computing the the min cut bound, okay, the minimum number of edges you need to remove from the network in order to disconnect S and T, while this number is also equal to the maximum number of edge-disjoint directed paths connecting S to T. Okay, so let's see an example. That's the butterfly. Okay, so what is the min cut between S and T1? So by definition, is the minimum number of edges you need to remove in order to disconnect them, and that minimum is 2. The theorem by Menger tells you that this number coincides with the largest possible number of edge-disjoint paths that you can obtain for connecting S and T1. And for example, here is one, and here is another one. These two are edge-disjoint, okay? And essentially the theorem tells you that you cannot find 3, okay? Or more, of course. So the min cut between S and T1 is 2. The minimum number of edges you need to remove, okay? But the theorem tells you that that's also the largest number of edge-disjoint directed paths. Okay, that's a very important theorem in graph theory. So one of the things you may want to remember from this presentation. And so how do we use Menger's theorem within the proof of the max flow min cut theorem? So there is part 1 of the statement which says, without loss of generality, and I said before, it's very important actually part of the theorem. So without loss of generality, all the matrices are a square of size n by n. And that's very important because otherwise, well, I cannot really state part 2. Okay, so we use actually Menger's theorem for that part. Okay, and so it's used actually to select the edges over which communication will take place. Okay, so you're gonna, by computing the min cut between the source and then the terminals, you know that this min cut is also the largest number of edge-disjoint paths connecting source and say terminal 1. Then you're gonna take those paths and then you're only using those for communication between source and terminal 1. Okay, so first application of Menger's theorem in network coding is selecting the edges over which communication takes place. Okay, and that's precisely what allows you to assume without loss of generality that all your matrices have the same size n by n. Okay, so here's where it is used. But then, okay, so we made all the matrices of size n by n, but then second part of the theorem, probably the most important one, tells you that these matrices are invertible, right? And then now we need an invertibility result for the GTs. Okay, and that comes from algebra instead. Okay, so the right size is given by the Menger's theorem, as I said, and then for the invertibility, we ask algebra this time. And so, as I said, the communication is going to take place on the edges and vertices, therefore, selected by Menger's theorem. Okay, and then we are using linear combinations, linear operations at the intermediate nodes, which we can describe as matrices. Okay, so linear maps, sorry, and therefore matrices. Okay, which we want to determine, of course. Okay, and in order to look for them, we use unknown for the entries. So I have a picture to explain this. So here I have the source that starts sending messages, and by this matrix attached to the source, which is unknown and I want to determine, I mean that the source is going to recombine messages V1 and V2 according to this matrix. Okay, and then, of course, by definition, every linear combination, a linear operation performed by a node can be described by such a matrix. Okay, so this matrix just means that the source is going to recombine the messages according to this rule. Okay, and then the outcome is going to be transmitted over the outgoing edges. And I do exactly the same for each of the nodes. Okay, and the size of these matrices depend on the number of incoming and outgoing edges. And these are variables because I want to find out what the matrices are, or one choice of the matrices. And then, well, the transfer matrices, which are all square, now we know that by Menger's theorem, Okay, so if you do if you like let the communication go, you will see that each transfer matrix this time is, well, n by m, and the entries are polynomials in the variables I picked for the entries of the intermediate matrices. Okay, and then now simultaneous invertibility of all the matrices, of course, it translates into the product of their determinants being non-zero, right? Because a matrix is invertible if and only if its determinant is non-zero. But then I have a bunch of matrices and I want all of them to be invertible. And this is the same as saying that the product of their determinants is non-zero. Okay, and then we need a result that guarantees that a certain multivariate polynomial, the product of all the determinants, has at least a non-zero. Okay, so, and that's the sparse zero lemma, which is the algebra result that I mentioned that kicks in the second part of the proof. And it reads as follows. So let P be a polynomial in a certain number of variables, L coefficients in FQ. And then suppose that the degree of P in each variable is upper bounded by D. And then if Q is at least D, so again a constraint on the field size, which then translates into the assumption that I have in the theorem of the max flow mean cut result in the statement of the max flow mean cut theorem. So if Q is strictly bigger than D, then there exists a certain element of FQ to the L over which at which the polynomial evaluates in a non-zero thing. Okay. So yeah, so the main idea of using the sparse zero lemma is this. So you attach matrices to each intermediate node. You label them. So each of the entries is labeled by a variable because you want to find them. So now the transfer matrices are n by n, and they have polynomials as entries. And now you want all of them to be invertible at the same time, and then you impose that the product of their determinants is non-zero. This is now a polynomial equation, and you want to find a non-zero of that. And the sparse zero lemma tells you that such a non-zero exists. So as I said, the proof is a little bit technical, and so if you want to write down all the details, it gets a little bit heavy notationally, so I decided to skip the proof, but I wanted to give you an idea of the argument and particularly mention these two key results that enter into the proof. Also, it's very nice that you combine kind of, graph theory result with an algebra one together in order to get an information theory achievement result. Yeah, so the sparse zero lemma concludes my first lecture. And yeah, that's it. Thanks a lot for listening.
Thank you very much, Alberto. It's very nice talk. It's open for questions. Anybody has any questions, please either unmute or type in the chat box. So, Alberto, will you share the slides with us at some point of time? And
oh, yeah.
Okay.
Yeah, I can share the slides.
And if you permit us, we can make them available on the workshop webpage.
Yeah, of course. Yeah. No problem about that.
Okay. Thank you. I mean, I only see compliments in the chat box, so with that.
Yeah, if you have any questions, you can also ask them next time or write to me. It's yeah, I didn't expect like many technical questions because this is more an overview of like why rank metric codes are relevant, essentially.
Yeah.
The next lectures are gonna be not with slides, but I plan to share the screen of my tablet and then write on that.
Wonderful.
Excuse me, sir.
Yeah.
Sir, while explaining this rank metric code, like how the distance is, the error is propagating but not amplifying. Can you please elaborate a bit more on it?
Yeah. So that lies in the theorem by Silva, Kötter, and Shishang, okay, that I stated at some point. So I'm going to go back to that. This one. Okay. So, well, let's go back to the picture before. Okay. So here I said that. So is this part clear that if just one vector is corrupted here, then because of these recombining things, you can end up with many corrupted vectors at the very end. So is this clear that from one you can go to 5? Okay, so that's clear. Now, so Silva Kutanashishon, they suggest you to kind of measure things in a different way. Okay, so they say, well, X, remember, is the matrix whose rows are the vectors. Okay, the messages, the original messages, and then Y of T is the matrix whose rows are the received vectors. Okay, and then G by X, GT by X is what you should receive if no adversary, the adversary doesn't do anything. Okay, then this theorem tells you that if at most T edges were corrupted, so in the example, just one edge was corrupted, okay, then the rank distance between Y of T and GT by X is no more than T, so no more than 1 in the example before, okay? Whereas if you wanted to measure what happened before in a kind of Hamming type metric, right, you should say, well, this edge, the value of this edge is different, then the value of this edge is different, the value of this edge is different, of this edge is different, and then the same, right? And then you're going to have a Hamming distance somehow of 5. Okay, so you start from one error and you get a Hamming discrepancy between the two matrices, the one that that was actually received and the one that was supposed to be received, okay, of 5, okay, over 6 rows. Okay, and then instead in the rank metric, the discrepancy, the rank discrepancy is going to be upper bounded by 1. So is that more clear now?
Yeah, yes, sir. Thank you, sir.
No worries.
I'm just saying there are more compliments in the chat box.
Yeah, I'm not super good with the chat, but yeah, now I'm opening it.
I think you will have to share and then, okay, let me ask one more time if there is any other question or comment that anybody has.
Also, thanks to all the friends and colleagues who joined the presentation.
All right, looks like none. So again, it's time for a break. So we kind of refresh ourselves and come back, and then I guess it's me who's giving the next talk, which is second part of my basic lecture on linear codes and linear codes. Thank you, and see you in about 28 minutes or so.
Thanks. Bye-bye.
Bye. So I just want to do an experiment. Let me see if I succeed.
अजून 5 मिनिट आहेत सर.
हाँ मैं जस्ट एक मेरा टैबलेट कनेक्ट करायचा प्रयत्न करतो. Okay, so I think I cannot quite do that. Let me just see. Do it some other way. Okay. Can you see me?
Yes, sir, we can see you, but camera is not clear.
It's too big, is it?
Yeah, camera is not straight. Now it's okay.
So, all right. So, this I just connected my tablet instead of laptop, which I was doing earlier.
Okay.
Let me try this. Let me share my screen.
Yes, sir.
It's not yet coming, no?
Yeah, I think it takes time.
I want to share is
Now we can see the screen. Yes, it's okay.
You can see this?
Now I can see. Yeah,
Okay. And I suppose you don't see me anymore.
No, yeah, we can't see you, but slides
It's
are
perfectly fine. I'm not much to look at. But the slides are not too bad.
Yeah.
Okay. I mean, I will. Okay. I'll just see if I can connect in another thing so that I can see the chat.
There is a chance of echo. There can be a chance of echo.
Okay. I guess you see me now?
Yes, sir. Yes. Yes, sir.
But then you see two presentations or not? This one?
Yes, we can see your presentation as well as you. Both.
No.
Now you are in a mute in one PC, right? In one terminal you are mute.
No, but do you see my presentation in two terminals?
Yes. No. In one terminal you can see presentation.
Okay.
And in another table, we can see you.
Me. You still see my presentation in two screens. No?
Yes, yes. We can see your presentation as a U.
Okay, so now let me see what happens if I change it. You see that changed?
Yeah, yeah. Yes, slides are changing.
Okay. All right. Okay, I think it's almost time. And this is my second lecture. I don't need an introduction. So, if Arun, if you allow me, I can begin. Maybe there is 1 minute.
Yeah, sir. Just 1 minute.
Actually, this is an experiment. I'm sort of trying for the first time to connect two devices. And
so one is your laptop.
Yeah, one is my laptop, one is and another is an iPad.
So laptop camera, you're using camera of laptop and iPad for writing.
Yeah, something like that. But if things, it messes up, then you tell me and I will. Okay. Can I begin?
Yes, sir.
Okay, so this is the second of my sort of general lecture on giving a quick introduction to basics of linear codes and with some emphasis on read-Miller codes. I didn't talk about read-Miller codes in the last lecture. In fact, this is the same set of slides. I'm going to go very quickly. We talked about genesis of coding theory. We talked about what is a general code or nonlinear code, singleton bound we proved. We talked about linear codes, MDS codes. I'm sorry, because of the process, it is taking some time. We talked about generator and parity check matrices. We related that to minimum distance. We talked about duality. Duals, what does it mean to say taking dual of a code? I told you what is spectrum and weight enumerator polynomial. Then I sort of motivated for you the Mac-Williams identity, proved in a special case. And then a general case of that was then stated and then used it to prove the Mac-Williams identity in a form that most of us are familiar with. So that relates the weight enumerator polynomial of a code to that of its dual. Okay, it's a beautiful relationship. All right, so that was proved. And then I gave some examples, the simplest of codes, simplex codes, Hamming codes, talked about their minimum distance, etc. I talked very briefly about Reed-Solomon codes, and Peter then talked about it in greater detail. I also talked very briefly about cyclic codes, basically defined for you what does it mean to say that a code is cyclic. And I pointed out towards the end of the last lecture that cyclic codes precisely corresponds to ideals in the quotient of the polynomial ring in one variable by the ideal generated by x to the power n minus 1. Cyclic codes of length n precisely correspond to ideals in this quotient ring. And as ideals in the quotient ring, they will have a unique sort of generator which comes from a monic polynomial that divides x to the n minus 1, and that's what is called the generator polynomial. In general, the code has dimension k, the generator polynomial has degree n minus k. And you can explicitly write down the generator matrix by taking these coefficients of this generator polynomial and shifting them one by one about k times so that you get a k cross n matrix. You can also write down the parity check matrix rather explicitly what you have to do is you have to divide x to the n minus 1 by gx. But then you also have to take the reciprocal polynomial of that. And that up to a constant will actually give you the generator polynomial of the dual. And so if you sort of write down the similar matrix with the coefficients of this polynomial, see gx has degree n minus k, this hx will have degree k, and so would its reciprocal. Reciprocal just means it will be hk plus hk minus 1 x and so on up to h naught x to the power k. So you get this parity check matrix, and you sort of make the leading coefficient 1, divide by 1 over h0, multiply by 1 over h0, then you get the generator polynomial of that cyclic code. So what in particular, duals of cyclic codes are cyclic, and you can also explicitly get the generator polynomials out of the generator polynomials of the original code. And cyclic codes is a big topic in coding theory, and a lot of people do a lot of things. What I've given you is just a very quick introduction, and you can refer to any of the books I mentioned for more on these. These are exercises, I think, which are doable by any reasonable student. So you can try them. Okay. So next basic topic I wanted to cover in coding theory is about bounds. There are all kinds of bounds, and many of them play an important role in our understanding of linear codes. So one basic bound is what is called Grismer bound. So what is a Grismer bound? So start with the NKD code, query NKD code. What does that mean? That means a linear code of length n, dimension k, and minimum distance d. Okay. Then it says that this n is greater than or equal to the summation from I going from 0 to k minus 1 of these ceilings. Okay, so this is the Grismer bound. So remember the ceiling, ceiling of a number is the least integer greater than or equal to that. So for example, ceiling of 1.5 would be 2. That's as opposed to the floor or the integer part, which is 1. So what is used here is ceiling. Okay, this takes a little bit of work to prove it. You can refer to the brief set of notes of mine that I mentioned in the last lecture, or any of the books that I mentioned at the beginning. Okay, just want to quickly point out that singleton bound is also an immediate corollary of this. Why is that? Because you look at this right hand side. So that is like dq to the 0 plus ceiling of dq and so on, dq square. And of course, this is d. And then whatever it is greater than or equal to 1. Okay, because it's of course positive. So you have 1 plus 1 added to itself. How many times? K minus 1 times, I going from 1 to k minus 1. So you just get that n is bigger than or equal to d plus k minus 1, or d is less than or equal to n minus k plus 1. That's the singleton bound. The simplex codes that I mentioned as an example, there this inequality is an equality. So they meet the Grismer bound. Okay, I want to talk about other set of bounds, which is which has to do with how the basic question is this: how large can a code be given some desired properties? For example, you say that for given parameters, basic parameters are length, dimension, and minimum distance. Okay, so it is sort of customary to look at the following function. You look at this a sub q and d, which we saw in the beginning of the first lecture, which is the maximum size possible of a query code of length n and minimum distance d. Okay, so what is the biggest size possible? And one kind of bound on this was given by the singleton bound. On the other hand, if you're only interested in linear codes, then you restrict yourself to the set of linear codes of given length and given minimum distance, and then you get a new function which is bq and d. Of course, the second set is smaller than the first set. So the maximum in the first set could be potentially bigger. So BQ is always less than or equal to AQ. And so see what Singleton bound did was to give a lower bound on this AQND. And what we will do now is to give an upper bound. Okay. So, and the idea there is to pack your code C with as many spheres of given the radius as possible. So I have to explain what is a sphere. So let me. So I mean, really, the correct.
Sir, your voice is not clear, sir. So sometimes it's breaking.
My voice. I see. So should I stop this experiment or should I stop the thing on the laptop? Can you hear me now?
No,
not really.
Whether it is due to laptop or due to presentation, I do not know.
Okay. Let me do one thing. Let me just turn off the thing in the laptop. Okay, you don't need to see me. And then let's see if the voice improves.
Okay.
Can you hear me better?
No, yes.
No, it's much clearer?
Yes.
Okay, so let's just continue with that. Okay, I can bring on myself in the end through the laptop. Okay, so I was talking about spheres, so which is really solid sphere. So what does that mean? So that means you take a point, let's say, excuse me, take a point X and just take some radius T and take everything inside. So that means points there are some Y which are at a distance T or less from the center X. So this is called a sphere of radius T centered at X, or solid sphere if you like. As I said, a better word should have been ball of radius T centered at X. Anyway, and D is of course the Hamming distance. Okay. So what do you do? So, well, because you are in the finite world, it's not, so you can actually count how many points are there. How do you do that? Well, you take your center X, this is the center X, and radius is T. So the Hamming distance of anything will be some number between 0 to T. Okay. So suppose the Hamming distance is exactly I. So things on, now if you like this circle or the of radius I. So how many code words can be there at Hamming distance I from X? So what does that mean? I have some coordinates for X, X1 to Xn, and I just take I have to choose Y1 to Yn so that X and Y differ in exactly I coordinates. Okay, so which means they have to be equal in n minus I coordinates. So I choose some n minus I coordinates where they are equal, which is equivalent to saying I choose I coordinates where they are unequal, and so that can be done in n choose I ways here. And now in the other I positions, I have to put an element which is different from the coordinate in X. So whatever is the coordinate in X, you don't take that. So you have q minus 1 possibilities for each of those I positions. So things on this, so to speak, circle of radius I will be n choose I q minus 1 to the I, and you add it up, and then you will get the cardinality of the circle. This is often denoted by V, motivation coming from geometry, where you're sort of thinking of it as the volume of that sphere. Okay, so I will use this notation that V, Q, and T will denote the number of points in the sphere of radius T is centered at a point, and you see that the right hand side is independent of the center. So it really just depends on the radius and the space you're in. Okay, so the Hamming bound or the sphere packing bound for codes, which is actually for general codes, says that this AQ and D is bounded on the right by Q to the power n divided by the volume of a sphere of radius T, where T is something specific. T is the integer part of d minus 1 over 2. Okay, maybe this is not difficult to prove, so let me quickly outline a proof of this. So what do I have to show? I have to sort of get a bound on the size of C. So take a code, query code, not necessarily linear, of a length n and minimum distance d. Okay. Now, so what you observe is that if I take some point, some code word C in C, okay, and I take a sphere, I'm sorry, my spheres look ugly, of radius t, and if I, let's say, maybe take 2 points, C1 and C2, okay, then I claim that the spheres are disjoint. Why is that? Because suppose there was a point in common. You know, suppose this sphere looked like that. Maybe this is C2. Okay? And suppose there was something in common. Then what would happen? The distance of that common point from C1 would be at most t, and distance of that common point from C2 would be at most t. So that would mean that the distance between C1 and C2 by triangle inequality would be at most 2t. But t is this. T is d minus 1 over 2. So 2 times t will be less than or equal to d minus 1. But then that's not possible unless C1 is equal to C2, because d was the minimum distance. So minimum of distance between two distinct points. So if C1 is not equal to C2, the spheres are disjoint. What that means is that the disjoint union of all these t spheres centered at points of the code is sitting inside the Hamming space at q to the n. So now if you take the cardinality of both sides, cardinality of the right hand side is q to the power n. Cardinality of this disjoint union is cardinality of each sphere, which is independent of the center. So that's VQNT. And that added to itself as many times as there are elements in C. So that's size of C. So you get cardinality of C times VQNT is less equal this. In other words, size of C is less equal this quotient. And since C was a perfectly arbitrary query code of length n and minimum distance d, I get this bound. Okay, so that's just the proof. Okay, this kind of leads to an interesting question: is when is this bound exact? Okay, that means this codes for which size of this thing here, this inequality should be an equality. So if that happens, then the code is called perfect. So code that meets the sphere packing bound is called perfect. So basically what happens there is that these disjoint spheres give you a perfect packing of the code C. Not only you know, yeah. So so you can yeah, you can. I mean, what are the examples of some examples of perfect codes? Well, there are trivial examples to begin with: the zero code and the full space. The Hamming code, which I mentioned, is an example of perfect code. I'll just illustrate it in the binary case, q equal to 2. So, so what happens there? So remember, it is of length q to the r minus 1 divided by q minus 1. Q is 2 here, so the length will be just 2 to the r minus 1. And I'm taking the minimum distance we already observed is 3. That means, and so d minus 1 upon 2, which is our t, that will be integer part of 2 upon 2, which is 1. So t is just 1. So size of a sphere will be like centered at any point, let's say even the origin doesn't matter, will be by this formula that we had, summation n choose I q minus 1 to the power I. It will be n choose 0 q minus 1 to the power 0 plus n choose 1 times q minus 1. T is just 1, I is going from 0 to t. So there are only 2 terms, and that will add up to 2 to the power r, because n is 2 to the power r minus 1. Okay. So what that kind of tells you is that this m times 2 to the power r, which is the size of the sphere, is exactly the full Hamming space, which means these spheres cover the Hamming space. Okay. So this is a perfect code. Okay. If you like this kind of an example, you can try to show it in general, that the Hamming code is perfect in general. And people have searched a lot for other classes of perfect codes, and I just mentioned one word. There is something called Golay codes, and certain Golay codes are known to be perfect. but I really don't have time to talk about that. But I just want to say that perfect codes are not easy to come by. And this is exactly what we see in real life. I mean, perfection is rare. You may strive for it, but it's not very often that you find perfection. Anyway, sphere covering bound. So this is the other type of bound. So first I had the sphere packing bound, and now I have a sphere covering bound. So this is also known as Gilbert bound. I'm just going to state it. It's a very fine lower bound for AQND, that it is bigger than or equal to. See, we saw that AQND is less than or equal to, what was it? Q to the N over VQNT. And now this is telling you that AQND is bigger than or equal to Q to the power N divided by a much larger denominator now, VQND minus 1. Okay. And you can also rewrite this by taking log to the base Q of both sides. So logarithm of this AQ will be greater than or equal to, now you use the properties of log, so N minus logarithm of this volume. Okay. As I said, I will not prove this, or well, why not? I mean, I have outlined a proof in the slides. I thought I will, no. Okay. Yeah, well, okay, oh, this one, okay. So this is for nonlinear codes. Okay, so this is not so difficult actually. So here is what you do. So you take a code of length n and a finite alphabet c. Remember, this is about AQ. That means the code can be nonlinear. It's a general code. So suppose its size is capital N. Okay, and what I'm doing is I'm taking, because this is maximum, there'll be some code C which meets that bound. Everything is finite. So let us suppose C is that code, so that its size is exactly equal to AQND. Okay, so in other words, it's an optimal code. So what that means is that for a given minimum distance, I cannot find a code of a bigger size. In particular, if I take some vector in Q to the power N, okay, then the distance of X to Ci must be strictly less than D for some I. Why is that? Because suppose the distance with every Ci were bigger than or equal to D. What would that mean? That would mean that if I add X to C, then minimum distance is still D. Okay, because adding X is not lowering your minimum distance. Okay, if distance of X with Ci were greater than or equal to D for every I. So then but of course C union with X has one more element than C. So that would contradict the fact that it has maximal size. So that gives you the distance of X with some code word is strictly less than D, Hamming distance. What does that mean? That means that everything in Qn is in a sphere of radius. So strictly less than D means less equal D minus 1. Is in a sphere of radius D minus 1 centered at some point Ci of the code C. So it means that the Hamming space is covered by this union of spheres. Okay. Now you take the cardinalities of both sides. So the left-hand side cardinality is Q to the power N. The right-hand side cardinality, this may not be a disjoint union, but the cardinality of union is of course less than or equal to the sum of the cardinality. So it's a sum of these volumes. And since this is independent of the choice of, doesn't depend on I, so this is M times VQ and D minus 1. And that's, if you sort of put that together, you have this inequality here. So, all right. So that's a short proof of the sphere covering bound. Very good. What you can do is you can actually do a little bit better if you're only interested in linear codes. And this result I'm only going to state that you can have this kind of a bound for BQ and D. What I've written in the first inequality is a little bit technical. Let me not even try to read it. But in the second inequality, it's a bound which is looking very much like the Gilbert bound, but with one less dimension, sort of n minus 1 d minus 2 rather than n d minus 1. So here the denominator is large, here the denominator is relatively small. So being a lower bound, it is a better bound. Okay, as I said. So the reason I mention it is because you can work your way around this, and it gives you some important asymptotic bound, which is for the largest possible rate. I don't remember if I said what is the rate, the rate of a code is just k upon n, is dimension upon the length. Okay, so you use one sort of criteria for a code to be good is that the rate should be as close to 1 as you want, and you also want the relative distance, which is d upon n, to be as close to 1 as you want. These are kind of conflicting requirements, and meeting them simultaneously is not easy. So you try your best to do as best as you can. So there are all these asymptotic bounds, and if you open any serious book on coding theory, you will find a lot of discussion of these. Okay, so I'm just going to be content with a mere mention here that there is this entropy function which is involved here and so on. So all these bounds feed into that asymptotic bound. Okay, it's not difficult, it's just a little technical. Okay. Very good. Yesterday somebody was asking about equivalences and so on, and let me just briefly mention about the notions of equivalences that exist in code. In some sense, this comes in 3 flavors: vanilla, strawberry, and chocolate, or if you like, permutation, monomial, and semilinear. So let me explain what is meant by equivalence. Okay, so suppose I have 2 codes, C1 and C2, both have the same length n. Then I say that they are permutation equivalent if you can get one from another by just permuting coordinates. That means there is a permutation sigma such that every code word in C2 is obtained from a code word in C1 by permuting the coordinates by this fixed permutation. So you permute the coordinates by some fixed permutation and let this vector x1 to xn vary over all of C1, then you get all of C2. If that happens, then C1 and C2 are equivalent. So yesterday we talked about generator matrices. So for example, if I take one generator matrix and I permute the columns, then I'll get another code that you will see is a permutation equivalent to the given code. Okay, that's an easy exercise. Okay, so another way of putting it is that if I look at this map, x1 to xn going to x sigma 1 to x sigma n, then that's obviously a bijection, in fact, a linear bijection of fq to the n to fq to the n. So linear isomorphism. And what you are saying is that this induces an isomorphism of C1 onto C2. Okay, so yet another way to say this would be that 2 linear codes are permutation equivalent if there exists a permutation matrix P such that if I send x is an element of C1, that means sitting inside fq to the n, think of it as a row vector, and multiply it on the right by this n cross n permutation matrix. So that will give you another row vector, another element of fq to the power n. That map should give you a bijection of C1 onto C2. Okay, so I sometimes use the notation C1, this tilde C2, if they are permutation equivalent. Okay, right. Then there is a, I will explain to you why we are taking this kind of equivalences and not a general linear map. The point is that if I C1 and C2 are k-dimensional vector spaces over fq to the power n. And of course, in linear algebra, you learned that any 2 finite dimensional vector spaces are isomorphic as long as they have the same dimension. But then you see that kind of isomorphism will not preserve the important Hamming distance and so on. Whereas permutation, as you can easily see, does not alter the Hamming weight. Okay, so it is indeed an isometry, as I shall explain. Another operation which will not alter the Hamming weight is multiplying some coordinates by a non-zero constant. Okay, so you can look at something which is a little bit more general than a permutation matrix, namely what is called a monomial matrix. So what's a monomial matrix? I'll explain. Monomial matrix, okay, so maybe let's do that first. A monomial matrix, yeah, I've done that actually. A monomial matrix is a permutation matrix multiplied on the right, let us say, by a diagonal matrix with non-zero diagonal entries. What that means is permutation matrix, you have exactly one non-zero entry in each row and each column, and that non-zero entry is 1, and the placement of this non-zero entry is a permutation. all you are now requiring is that non-zero entry could be anything non-zero and not necessarily 1. Such a thing is called a monomial matrix. So what you do is instead of x times p, you just take x times m, and so x times m, x going to x times m gives you a bijection of C1 onto C2. And sometimes you use this notation, C1 approximately equal to C2, to indicate that they are monomial equivalent. So this noise I was making about isometry, what is an isometry? You know this from geometry. That means just a bijective map which is distance preserving. That means distance between x and y should be same as distance between fx and fy. And that's called an isometry. Here distance is the Hamming distance. Okay. So, and you will see it's not difficult to see that so suppose I have a linear and bijective map, then it is easy to see that instead of saying, if the map is known to be linear, then it will map 0 to 0. So saying that it is distance preserving is same thing as saying that it is Hamming weight preserving. Okay, so if it is a linear and bijective map, then it's isometry if and only it preserves the Hamming weight. So this is just a simple observation, but now, and that's the kind of maps you want. You see, you want maps which preserve the Hamming weight, etc. Okay, and if you the point is that if you require such a bijection to be linear, then it has to be something which is coming from a monomial matrix. So that means if we have a linear isometry, okay, if you have a linear isometry, a linear isomorphism which preserves distance, which preserves Hamming weight, then it is necessarily given by multiplication on the right by a monomial matrix. There exists a monomial matrix so that fx is given by x times it. How do you see this? Well, it's not difficult. Suppose you have a linear isometry. Okay, you take the standard basis of fq to the n. That means 1, 0, 0, 0, 1, 0, etc., etc. Now remember, so what is EI? EI is something of Hamming weight 1. Because it is Hamming weight preserving, EI has to go to some code word, some element of fq to the n of Hamming weight 1. But what are the elements of Hamming weight 1? That just means one non-zero coordinate. These are nothing but non-zero scalar multiples of the standard basis. So this will be some constant times Ej. Okay, and because this is a bijection, this J will be uniquely determined by I. In other words, this J as corresponding to I, as I varies from 1 to n, will be a permutation of 1 to n. So what that shows is that there is a unique permutation sigma such that f of EI is lambda I times E sigma I, where lambda is a non-zero constant and sigma is a permutation. And now you are done because you just take the corresponding permutation matrix and you take the diagonal matrix corresponding to the lambdas, and you can check easily that with this condition I must have, because any x will be a linear combination of the EIs, and effect of that will be multiplying by this monomial matrix M. So that's sort of indicates to you why it is natural to look at equivalences by monomial matrices. I just want to mention, okay, let me make some remarks. When you are over binary, the permutation and monomial equivalences coincide. Why? Because what are the non-zero element in F2s? There is just one. So multiplying by one doesn't really change things. Okay, so it's just the same notion. Okay, if two codes are equivalent, they have the same parameters, same length, same dimension, same minimum distance, same spectrum, same generalized Hamming weight, etc. Okay, and I think I said already, if two codes are monomial equivalent and you have a generator matrix of 1, then if you multiply it by on the right by this M, you get a generator matrix of another. So in particular, you can swap the columns of the generator matrix and you will see that any code is permutation equivalent, in fact, to a code whose generator matrix is in standard form, or what Peter Beelan called a systematic form. Okay. Now, I talked about equivalence of one code with another. You just take C1 equal to C2, and then you get the notion of automorphisms of codes, which is very important. So you can talk, and that will form a group. So permutation automorphism group is those permutations sigma, so that if you permute the coordinates of a code word x1 to xn by this permutation sigma, you again land up in the same code. So basically, those sigma, so that the corresponding f sigma is a linear bijection of C onto itself. Okay, so this is called the permutation automorphism group, and this is obviously a subgroup of the symmetric group on n letters. Okay, another way to think about the permutation automorphism group is to think of it as a subgroup of GNN, n cross n non-singular matrices, where instead of permutations, you just take those permutation matrices so that x times p is in C for every x in C. Okay, so we often think of permutation automorphism group as a subgroup of the group GLN of non-singular matrices. And then there is something called monomial automorphism group. Well, it is just the set of monomial matrices, so that x times m, so that x times m is in C for every x is in C. And that's also a subgroup of GLN. And now I should like to tell you about a third type of automorphism, which is the most general, and there is also corresponding notion of equivalence. So that is called semilinear automorphism group. Okay, so let me explain that. So I have P aught, M aught, and gamma aught. This is the third and most general flavor. So what you do is, see, apart from permuting coordinates, multiplying by non-zero constant, there is another operation which also preserves, preserves the Hamming weights. For example, if I raise everything to pth power, my q is a power of prime p. Okay, then that doesn't change. So in other words, if I sort of twist things by a field automorphism of fq, so I take not just a monomial matrix but also a field automorphism, and I look at those such products so that whenever x is in C, x times mu is also in C, then that constitutes a group that is called the semilinear automorphism group of C. Okay, so what do I mean? So mu is a automorphism of fq. So if you know your field theory, you can also think of it as the Galois group of fq over the prime field fp. And whenever I have a vector y like x times m, y mu will just means acting mu on each of the coordinates. Okay. I explained to you why monomial maps are natural, because they exactly correspond to linear isometries. Similarly, you have a result for semilinear isomorphisms. So this is just a general discussion of what is a semilinear isomorphism of one vector space to another. The linearity is preserved as far as addition is concerned, but when it comes to scalar multiplication, f of a times x is not a fx, but instead mu a fx, where mu is some automorphism of the field, of the scalar field. Okay, such maps are called mu semilinear, or semilinear if it is mu semilinear for some reason. Okay, and if it is a bijection, then you call it a semilinear isomorphism. Okay, and the set of all semilinear isomorphism of the Hamming space onto itself will form a group which is usually denoted by gamma LNQ. Okay, and this gamma aught is a subgroup of that. And the theorem of Mac-Williams, it's a beautiful theorem which says that if I have two linear codes of length n, and for technical reasons you assume that the dimension is at least 3, and suppose you have a map of one code to another, then that map is a weight preserving bijection. It preserves Hamming weight, and not only that, but it also preserves, it sort of maps r-dimensional subcodes of one to r-dimensional subcodes of another, okay, for every r. And that happens if and only if f from C1 to C2 is a semilinear isomorphism. Okay, so that sort of, the reason I have to say that it maps r-dimensional subspaces to r-dimensional subspaces is because my f is not assumed to be linear. Okay, indeed, it can be semilinear and it will do this property. And Mac-Williams sort of says the converse, that if you have a weight preserving bijection which maps r-dimensional subspace to r-dimensional subspaces, then it has to be a semilinear isomorphism. This proof is slightly involved. Some years ago, with another person, I gave a different proof, and if you're interested, I can tell you more about it. Okay, how much time do I have? So yeah, I have about 25 minutes. 20. So I want to know 23.
Yes.
23. Thank you. Thank you. I'll try to finish in time. So now I want to talk about Reed-Muller codes, which is one of my favorite classes of codes. And it's really rather ubiquitous in coding theory, and it's gaining more and more importance because of various reasons. It's a class of codes which was first studied by Irving Reed and Muller. In the same year, they wrote different papers, more or less referring to each other. But of course, they looked at the binary case. And the way it is defined in the binary case, there are various ways. There is a Boolean construction, or what is called Plotkin construction, etc. I will talk about the Reed-Muller code in a somewhat more general setup. First of all, in the query setup. And so what I'm calling Reed-Muller code is in the coding theory literature often called generalized Reed-Muller code. But I'll drop the word generalize. Okay. In any case, the classical Reed-Muller code would be a special case of this with Q equal to 2. Sometimes it's also called affine Reed-Muller code. And that should indicate to you that there is something called projective Reed-Muller code. But that's not a class which I'm talking about. That's also an interesting class of codes, but somewhat more difficult. Okay. So, and I think the fundamental papers on this topic are those of Kasami, Lin, and Peterson in '68, and a very nice paper of Delsart, Goethals, and McWilliams in 1970. All right. So, what is this Reed-Muller code? Okay. So, one way you can think about this is, you had the Reed-Solomon code, and that looked at polynomials in one variable of a degree less than or equal to something, say k minus 1, and you evaluated at some points. Okay. And that gave you a nice MDS code. But then in order to get that nice code, your Q had to be pretty large because you had to have enough points in FQ. Now, what if your Q is small? Maybe Q is 2. Then you really can't construct that Reed-Solomon code. But then instead of suppose my Q is small, I can still construct this Reed-Muller code, and it will be pretty interesting. What I do is, instead of looking at FQ, I go to the m-dimensional space over FQ to the power m. So I can take m as big as I want. So my Q could be 2, but 2 to the power m can be as large an integer as you want. And so you take that m-dimensional affine space, or set of all m tuples of elements of FQ. It's a finite set. How many elements does it have? It has Q to the m elements. So you list them. The first one is P1, then P2, and then say P sub Q to the power m, because there are Q to the power m elements. And now you do an evaluation map similar to Reed-Solomon. But now these are points in the m-dimensional space. So you will take, first of all, polynomials in m variables. Okay. Polynomials in m variables of degree less than or equal to some fixed number, let us say nu. So I take f in m variables, coefficients in FQ, degree less than or equal to nu. I denote the space of all such polynomials by this intuitive notation. FQ x1 to xm is polynomial ring in m variables. I put a subscript less equal nu to indicate that I'm taking those of degree less equal nu. By the way, by degree, I mean total degree here. All right. So now I can define the Reed-Muller code. So what I do is I now take this space and I take a polynomial in this space and simply evaluate it at each and every point of FQ to the power m. F of P1, F of P2, dot, 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 F of P sub Q to the m. So I get a huge tuple of length Q to the power m. And this map is obviously a linear map. F plus G goes to where it should go, and some constant times F should go to where it should go, etc. So this gives me a map from this space of polynomials of degree less equal nu to the space of all Q to the m tuples. And that's a linear map. So its image is a linear subspace of FQ Q to the m. And that image is called the Reed-Muller code. And we denote it by Rm sub Q nu comma m. If there are any question, you can ask me, because this is a basic definition. And unless you understand this, I cannot proceed too much. So Arun, if there is anything in the chat box, you just read it out to me.
At the moment, there's nothing in chat box.
It should be clear. After all, it's a very simple object. Okay. Let us talk about the basic parameters. So length and the dimension. So Well, length is obvious. Length is, you're looking at it. It's there are q to the m tuples. So length is obviously q to the power m. Okay. So you can construct pretty large codes here, even if your alphabet size is small. And now what about dimension? Well, to begin with, let us look at the dimension of the domain space. What is the domain space? Set of all polynomials of degree less equal nu in m variables. Obviously, that's a vector space. And a basis of that will be given by monomials in x1 to xm of degree less equal mu. So how does a monomial look like? Monomial will look like x1 to the power I1, x2 to the power I2, xm to the power Im. And to say that degree is less than or equal to mu would mean that the sum of the exponents should be less than or equal to mu. Right. So in other words, the cardinality of this set is same thing as the cardinality of the set of all m tuples of non-negative integers. N denotes for me set of non-negative integers whose sum is less than or equal to nu. And this is a well-known number. This is given by the binomial coefficient m plus nu choose nu. I think most of you should know that. If not, that's a good exercise. There are many ways to prove it. One way could be that you can do induction on m plus nu. It's like a double induction on m and nu. So of course, initial cases are easy, but if you want to do the induction step, what you can do is you take this set and you split it into two parts. One part is where Im is 0, those tuples where Im is 0, and another part where it is not 0. That means it is bigger than or equal to 1. So this part would correspond to monomials in m minus 1 variables of degree less than or equal to nu. That means what? So by induction hypothesis, m plus nu minus 1, choose nu minus 1. On the other hand, if I look at this Im bigger than or equal to 1, I can have a bijection of this second set with the set of tuples j1 to jm, so that j1 plus j2 plus jm is less than or equal to nu minus 1. I'm sorry, maybe the first thing I should have written, not that it is different, maybe I should have written it as m minus 1 plus nu, just for psychological reason, because it's m minus 1 variables. And I should have also written a nu here, because the degree is still nu. M minus 1, plus nu, sorry. And what about this one? So now you can kind of subtract Im. You can look at the tuple I1, I2, Im minus 1. And that's a tuple of non-negative integer whose sum will be less than or equal to nu minus 1. So this will be, again by induction hypothesis, m plus nu minus 1, choose nu minus 1. And now you use your Pascal triangle identity and you see that this is same as this. Okay. Very good. So that's as far as the domain is concerned. So that's a standard fact that the dimension is m plus nu choose nu. Okay. So that dimension of the domain will be same as the dimension of codomain, provided my linear map evaluation is injective. But question is it injective? And the answer, unfortunately, is no in general. This is not injective. And this is like an instance of so-called Fermat's little theorem. A to the power p is congruent to a mod p. Or in the finite field case, a to the power q is equal to a for every a in fq. So if I look at, for example, the polynomial x1 and x1 to the power q. As polynomials, they are obviously different polynomials. But when I substitute a value in fq, they give me the same number, because a to the power q is same as a in fq. Okay, so these two polynomials, although they are different, their evaluations, their image will be the same. So that means the map is not injective. Well, what do you do then? Okay, so one standard thing to do is you look at what are called reduced polynomials. This is the set where the map will be injective. Okay, so let me try to explain this. What is a reduced polynomial? So first I'll define for a monomial. Suppose I have a monomial. Okay, some product of variables. I call it to be reduced if I don't have any power which is q or more. That means every exponent alpha I is less than or equal to q minus 1. Then the monomial is reduced. Well, if every monomial appearing in a polynomial is reduced, then you say the polynomial is reduced. So reduced polynomial is just a FQ linear combination of reduced monomials. Okay, every term is sort of reduced. Every monomial appearing in it is a reduced one. Okay. Notice that if my total degree were less than q, strictly less than q, which means what? Say for every monomial appearing in there, I have alpha 1 plus alpha 2 plus alpha m strictly less than q, means less than or equal to q minus 1. Then obviously alpha I is less equal to q minus 1 for every I. So that will imply reduced, but the converse is not true. You can write down several reduced monomials whose degree is bigger than q. For example, I can write down x1 to the q minus 1, x2 to the q minus 1. Okay, and that will have degree 2q minus 2, and which is of course bigger than 2q in general, but the polynomial is still reduced. Okay, only thing you can say is that because I'm required to have alpha I less equal q minus 1 for all I, alpha 1 plus alpha 2 plus alpha m would be less than or equal to m times q minus 1, because each of them is less equal to q minus 1. So all you can say is that if f is reduced, then the total degree is less than or equal to m times q minus 1. Okay, very good. Now I want to just give you a little lemma. Suppose I have a reduced polynomial, okay, in the sense that I just defined, and suppose it vanishes at every point of fq to the power m. Then the lemma says it must be the zero polynomial. Okay, how do you prove it? Well, you can just induct on m. So m equal to 1. This is like polynomial in one variable. Okay, the polynomial in one variable, and it is reduced. So in one variable, reduced will also is same thing as saying degree is strictly less than q. So degree is less than q, and it has q roots. But you know that a non-zero polynomial of degree d has at most d roots in any field. Right, non-zero polynomial of degree d with coefficients in a field has at most d roots in that field. So, but it has more than d roots because degree is strictly less than q, and every point of q it vanishes. So it must be the zero polynomial. So m equal to 1 is easy. What about the general case? Suppose m is bigger than 1, and my result holds for polynomials in m minus 1 variables, or in fewer than m variables. What do I want to show? I just want to show that for a polynomial in m variables, which happens to be reduced, I should have, I want to show that it is the zero polynomial. So suppose, assume that it is reduced, and assume that it vanishes at every point of fq to the power m. What do? I want to do induction hypothesis, so I want to cut down the number of variables somehow. So what I will do is I will write it as a polynomial in one variable, coefficients polynomials in the remaining variable. So I write f as polynomial in xm, coefficients polynomials in x1 to xm minus 1. So because the degree in xm is q minus 1 or less, I can write it as something f0 times xm to the q minus 1 plus f1 xm to the q minus 2, and so on up to f sub q minus 1, where fi's are polynomials in all variables except the xm. So fi's are polynomials in x1 to xm minus 1, and incidentally fi's are also reduced. I'm sorry, there is a typo here. This should not be there. 0 less than or equal to I less than or equal to q minus 1. Okay. So now suppose I substitute some a1 to am minus 1 arbitrary m minus 1 tuples in f. Okay. Then what will I get? I will get then these fi's will get evaluated at that a1 to am minus 1, and I will then have a polynomial in xm with the coefficients in fq. So I have some object in one variable polynomial whose degree is less than or equal to q minus 1. But then I know that f vanishes at every point. You see, f vanishes at every point of fq to the m. So this guy has to be. So it's a polynomial in one variable, degree less equal q minus 1, and q roots. So it must be the zero polynomial. What does it mean to say that this is the zero polynomial? This one is the zero polynomial. Means fi, each coefficient is 0. Means fi evaluated at a1 to am minus 1 is 0 for every I. Okay, and for every and a1 to am minus 1 was arbitrary, so I get fi evaluated at those is 0. Now you apply the induction hypothesis, and that will imply that fi has to be the zero polynomial. So each coefficient as a polynomial in m minus 1 variables is the zero polynomial, and therefore f is the zero polynomial. So that proves this little lemma that for reduced polynomials, the evaluation map is injective. Okay. So as a corollary, we can find the dimension of the Reed-Muller code in the special case when nu is less than q. So if nu is less than q, evaluation is injective, and therefore this Reed-Muller code is isomorphic as a vector space to the space of polynomials. This one to this space of polynomials of degree less equal nu, whose dimension we have already seen to be m plus nu choose me. Okay, so I get formula for the dimension of the Reed-Muller code provided nu is less than q. Okay, that's immediate. I think I have written down the proof, but I already said it. All right. Now this reduction business is something that you can carry out in general. We have a natural map which takes monomials to reduce monomials. What do you do? Basically, what you do is the following. Moment you see q, you kind of replace it by 1. Okay, so in some sense, you're reducing mod q minus 1, but not completely, because if you see exponent q minus 1, you don't make it 0. Okay, that is not allowed. So what you do basically is you take, suppose you have a monomial like this. As long as if the exponent alpha I is between 0 and q minus 1, you just leave it unchanged. If it is q or more, then you divide by q minus 1 and look at the quotient and the remainder. Okay, but you know, I'm allowing here. I'm allowing, this is not exactly division algorithm, because my remainder I'm not allowing it to be 0, but instead I'm allowing it to be q minus 1. Okay, so I can if I write it as q, you see that you can always do that. You can write it as q minus 1 si plus ri for unique integers ri and si, where this ri is strictly greater than 0 and less than or equal to q minus 1. In the usual division algorithm, you usually have greater than or equal to 0 and strictly less than q minus 1. Well, instead of that 0, I'm allowing it to be q minus 1. Okay, and if you think about it, you'll realize why. So I take the exponent to be this ri. Okay, so basically all that I'm doing is I'm replacing this exponent alpha I by an exponent beta I, which is allowed to be less than or equal to q minus 1. Okay, and this is how you do it. So this is called the reduction map. So obviously this x1 to the beta 1, xm to the beta m is a reduced monomial. Okay, I have to hurry. I think I have 5 minutes or so. And then I extend it by linearity to whole of the polynomial ring. So because after all, every polynomial is a FQ linear combination of monomials. So the reduction of a polynomial f, I denote it by f bar. And this f bar is of course a reduced polynomial. And it has the property that its evaluation at any point is same as evaluation of f at p. That's more or less how it is constructed. That's Fermat's little theorem, if you like. Okay. So I will denote by R sub q, this German R sub q m comma nu, the space of all polynomials in m variables of degree less equal nu, which are reduced. So you see basically what this is exactly the image of this space of polynomials less equal nu under the reduction map, f going to f bar. So because I get, all right. I just want to make some observations that if nu happens to be bigger than or equal to m times q minus 1, then you know the space of all reduced polynomials is same as space of all reduced polynomials of degree m times q minus 1. Because reduced polynomial has degree at most m times q minus 1. We have seen that. So secondly, the evaluation of this space fq less equal x1 to xm less equal nu, because that is same thing as for the reduced polynomial. So the Reed-Muller code can be thought of as the image of the space of reduced polynomial. And second observation, using first one and the second one, which is a consequence of the first two, is the Reed-Muller code of order nu is same thing as Reed-Muller code of, oh, I'm sorry, there is a typo here. This should be mq minus 1 comma m. If nu is greater than or equal to m times q minus 1. So for these reasons, one only considers Reed-Miller code when nu is between 0 and m. Okay. So now let me at least explain to you, if you allow me, Arun, the dimension formula for Reed-Miller codes in general.
Yes, so we have 2 minutes.
Okay. Or so the formula is given by this nice or complicated expression depending on your viewpoint. Or maybe I shouldn't be rushed. I'll leave it in the slides. Basically, what this just comes from. What you need to do is you simply need to count the dimension of the space of reduced polynomials, and the way you do that is observe that you have to count all m tuples which add up to something less equal nu, and furthermore have the property that each ij is strictly less than q. Okay, is less than or equal to q minus 1, and you can count it by inclusion exclusion. I have written down a short proof because I don't want to be rushed. Maybe I will skip this, and I will also skip this curious identity which you get. But I want to just explain this small bound. Okay. You know that a polynomial of degree nu has in one variable has at most nu roots. What about polynomial in m variables? When you are over infinite field, of course it will have infinitely many roots in general. But when you are over finite field, your universe is finite, and if nu is less than q, you can show that it has at most nu times q to the power m minus 1 roots. So the way you can sort of intuitively think about this is that let's say I have the m space. This polynomial in m variables kind of gives me a surface or hypersurface. Suppose I project it on the codimension 1 hyperplane. Then given a point below, I have, because the degree is nu, they have I have some at most nu points above, and below that I have q to the power m minus 1 points. Above I have, this is like below every point I have at most nu points. So the total bound will be nu q to the power m minus 1. But then this needs a little bit rigorous proof, which is not difficult. Since I'm out of time, I will skip this. But I just want to say that if you give me that lemma, then it immediately follows that the minimum distance of the Reed-Miller code is given by this formula: q minus nu times q to the power m minus 1. Why is that? Just find the minimum Hamming weight. You take a non-zero code word, it looks like evaluation of some polynomial, okay? And such a polynomial, because I'm assuming nu less than q, so everything is reduced, will have, by the previous result, at most nu q to the power m minus 1 zeros. That means at least q to the m minus these many non-zeros coordinates. So Hamming weight of any non-zero thing is bigger than or equal to this. On the other hand, it's very easy to construct a polynomial which has exactly that many zeros. So I just take a polynomial x1 minus a1 to x1 minus a nu, but think of it as polynomial in m variables. So what are the zeros? x1 has to be one of the ai's. It can be chosen in new ways. x2 to xm are completely free. So they can be chosen in q to the m minus 1 ways. So total nu times q to the m minus 1, that is exactly these many roots. And that shows that you have a code word whose Hamming weight is this. So that proves that the minimum distance is q to the m minus nu q to the m minus 1, which is this. So that's the formula for minimum distance when nu is less than q. I mean, there is also a formula for the minimum distance when in the general case, okay. All right. So maybe you can ask many questions, but I will just show you this general case, some answers. This is a first theorem, which gives you the answer when nu is arbitrary, what is the minimum distance. The second theorem is another beautiful theorem about Reed-Miller codes, which says that duals of Reed-Miller codes are also Reed-Miller. And I would have liked to state the third theorem, which gives you a complete description of generalized Hamming weights, which is a beautiful result, originally due to Hein and Pelikan, but a new proof given by Bilan and Datta. But this will be explained to you by Mrunmay Datta. So I think I will stop here. Thank you very much. And sorry, I extended by 2 minutes, maybe.
Thank you, sir. Thank you. So there is one question by Sushil Kumar Azad.
Yeah.
So can you take an example? I think example of Reed-Miller codes or?
Sure. I mean, what see, all you have to do is to take give some small values of q, m, and nu.
Yeah.
Okay. So I mean, what is the Reed Miller code? You have I have called it RMQ nu m. Okay. So for example, m is equal to 2, and let us say nu is equal to 2. Okay. So I have variables x1 and x2. So what am I doing? I'm looking at polynomials of degree less than or equal to 2 in two variables. So there is a constant polynomial. There is x1, x2, x1 square, x2 square, and x1, x2. So I am taking a linear combination of these. Okay, and then I have some field fq. So I take a f, which is some linear combination. I don't know. Let's say c0 plus c1 plus c2 plus c3 plus c4 plus c5. Let us say. Okay, and I just evaluate it at points of. So I just look at f of p as p ranges over fq square. Okay, so for example, maybe you can take q is equal to 2 also. So what are the points? There are 4 points. So I will look at f of 0, 0, f of I don't know 1, 0, f of 0, 1, and f of 1, 1. Okay, so I will have a code of length 4 by evaluating these polynomials of degree less than or equal to 2 in two variables at these 4 points. Okay, you can try to figure out what you get. Actually, I just concocted this example. So that's an example of a Reed Miller code. But you can take a larger queue, and then you of course have a bigger tuple and a code of a bigger length. Does that answer your question, Azad?
Yes, he is saying yes.
Okay. Anything else?
No, sir. There's no question.
Okay. So then let me see. Maybe I will try to. I'll try to join on the laptop just to be visible and see you, but then remove this perhaps. Maybe I'll just do it the hard way. Okay, sorry. Sorry.
Yes. Yeah. Akash asks.
Now you can see me and hear me, but don't see the slides anymore, right?
Yes, but you can see chat also.
Hello?
Can you see chat, sir? Hello, sir. Can you see chat?
Misut has made a comment. Thank you, Misut. It's good to have you here virtually.
I think you cannot hear us. Can you hear us?
Hello, can you hear me?
Yeah. Sir.
Hello?
Hi, sir.
Can you hear me? Okay. Yeah, I think I was speaking a short while ago, but the laptop volume was, I put it down, but now it's okay. I think I can listen to you.
No, sir. Can you listen me?
Yeah, I can. I think, initially I couldn't because, when I used two devices, I had lowered the volume of laptop to 0. And I sort of forgot that. Right. So somebody wants to know if they will get the slides. Yes, I'll just correct the typos and I will make it available. Maybe I can even put it on the web page of the workshop. By the way, speaking of making slides available, yesterday in the lecture of Pante, somebody asked for his slides. He has sent it to us, but he has told us that he would prefer not to put it online, but instead to mail it to anybody who is interested. So if you're interested in his slides, maybe you can email to the conference address, and then we'll try to send it to you with the condition that you don't sort of share it publicly. Okay. When I was muted, I also personally thanked Mesut, who wrote a nice note, and I think just want to say that it's nice to see him virtually.
And to Raju Kumar also. Raju.
Oh yeah, Rajiv is also there. Okay, yeah, thanks, Rajiv. Okay.
Yes, sir. So there's a question.
Yes, there is a question.
Ritu Arora says thanks.
Sir, thank you very much.
Thank you.
Sir, in fact, you won't remember me, but my PhD thesis was examined by you. I'm Professor B.K. Das student. Yes, sir.
I remember now.
Yeah. Yes, sir.
What are you doing now?
So right now, nothing in research, but now, in fact, I'm planning to.
You were already teaching in college.
Yeah, I'm teaching. Otherwise, I'm working as associate professor in Delhi University. Yes.
Very good.
So now we are introducing one coding paper for the undergrads in the third year.
Okay.
So we are planning to take up that paper in the next year. So that's why revising everything now.
Yeah, so I hope this little workshop is helpful.
Yes, yes. This your lectures were quite fruitful. Yeah.
Okay. I guess it's break time now, probably.
Yes, sir. So
Happy to.
if there is no other question or comment, then we can have a break and then we can meet.
Right. So the next lecture will be at
6:30.
that means 20 minutes from now, 6:30 India time.
19 minutes, yes.
Okay. Okay, 19 minutes.
So next lecture will be by Professor Sarkar.
Yeah, Shantanu Sarkar. Actually, yeah, Shantanu Sarkar. Sartaj, are you there?
I think not.
Yes, I'm here.
Okay.
No, Sarkar is there. Sarkar is not there.
I know, but I was just saying
No.
maybe Sartaj can introduce.
Yeah, sure. Yeah.
Of course, I know him too very well. He's from IIT Madras, and right now he's giving this lecture from Germany, I believe.
Yeah.
Okay.
So he's Sartaj and he's Sarkar.
Yes.
Okay, sir. Then we can.
Okay. See you in a short while.
Sartaj, are you there?
Yes. Yes.
There is one question for you from me.
Okay.
Actually, we are live streaming on YouTube also, right?
Okay.
But what happens that live streaming? Why we consider, because the number of people may go beyond 250.
Okay.
And that is why we arrange YouTube live streaming.
Right.
But now we can see that the number of participants for class, the lectures are less than 250.
Okay.
So can we stop live streaming sessions from now onwards?
We can. I mean, so do you want me to?
We have to write one email to all the participants saying that no need to have live streaming, and you can join to directly to Google Meet link.
Yeah. So even if we, keep this live streaming things, so is there any problem in that?
Yeah. Continuously there should be a person sitting there, and he have to take care of so many things.
Oh, okay.
So he cannot move even for a small break.
Okay. So maybe then I will write.
Yeah, that will be good, because we have enough capacity inside this Google Meet link.
Okay, great.
Maybe from next lecture.
Let's plan it from tomorrow onwards, I think.
Okay, we will plan from tomorrow. Okay.
Yeah. Okay.
But maybe you can ask to sir also.
Yeah, I'll discuss with him, and then we'll take a decision.
Yes.
Okay. Hello, Santanu.
Hi, Sartaj.
Hi, how are you?
Yeah, fine.
So, is it late afternoon there or?
Yeah, now here is 2 o'clock.
2 o'clock. Okay, okay, great. So maybe you can.
There is 6:25 or something, right?
Yeah, here it is 6:25. Yes.
So let me come to presentation.
Yeah. You can try to share your slides and just check with it.
So your entire screen, where I have to go, because this is my first time.
For Google Meet.
Yeah.
Your entire screen. Yeah.
Entire screen. Okay.
Okay. Yeah. It takes some time actually.
Okay.
So just keep your presentation open. Yeah, it will take some time. Yeah, now we can see it. Yes.
Okay.
Yeah, if you want, you can make it full screen.
Yeah, I will make.
And also there is something called Meet Google is sharing your screen that just at the bottom. So you can hide it perhaps.
No, I don't. So are you getting my screen?
Yes. You can hide this. There is one line coming on. Now it is okay.
Okay. Then another thing I have to do. I have to open another window probably to see you. Otherwise, because I am seeing only my own presentation, nothing else.
Yeah, that's okay. But we are able to see you as well as your presentation.
Okay.
Yeah.
So, hi Shantanu.
Hi, just 1 second. I am not seeing you because I see only my presentation. Hi, how are you?
I'm fine. How are you? Thanks for doing this.
Thank you for inviting me.
Sure. So you're in Bochum, I understand, right?
Yeah. So basically, I am visiting Bochum in Missouri, but my wife is in Karlsruhe.
Okay.
That is different city. And currently, I am now in my wife's place.
Okay.
Because I have now 6 months child.
I see. Okay. So then,
most of the time I am staying here.
Both the parents.
Yeah.
Do you have 2 devices connected?
Yeah. Now are you?
Now it's okay.
Okay.
I think even I tried to do that little bit in my lecture, and then that's all.
Yeah, if I make full screen, then I cannot see you. That's the main problem. So I make 2 devices.
Yeah.
So we have 1 more minute actually. So
Yeah.
You and I think Rakhi has made a comment whether it's possible to have recorded video. Some of the speakers were not very keen to share the videos publicly. So and we have to respect their wishes.
Yeah, for me it's fine. You can record.
Okay. I think what my idea is that we will record, we will show it to speakers, and then if they sort of allow us, we share them. But
okay.
Yeah, so maybe we can start now.
Sure.
Yeah, we can start.
So okay, so it's my pleasure to introduce Professor Shantanu Sarkar. He did his PhD from Indian Statistical Institute, Kolkata, in the year 2011, perhaps, if I'm not correct. With Professor Subhay Maitra. And after that, he has been inspired faculty at Chennai Mathematical Institute for about 4 to 5 years. And then he moved to Indian Institute of Technology, Madras, where he's currently associate professor. And also, he's currently visiting Ruhr University, Bochum. I'm not sure if my pronunciation is correct.
Yeah.
And he's a very well-known researcher, and he has got several awards. For example,
a young scientist Platinum Jubilee Award in Physical Sciences in the year 2016, and several Best Paper Awards, and also he has been offered assistant professorship, associate professorship at various other institutes in India. And he is a well-known researcher not only in public key cryptography but also in symmetric key cryptography. With this brief introduction, I would request Professor Shantanu Sarkar to begin with his lecture.
Thank you, Sartaj, and thank you, Professor Sudhir Gorpare, for inviting me. So can you hear me?
Yes.
Yeah, thank you. So, okay, so let me then start. So my plan is to discuss public key cryptography, and mainly I will discuss RSA crypto system, because we cannot cover all public key. So I discuss RSA crypto system, and we will focus mainly on RSA and how we can attack in some situation. Of course, RSA is still secure. We cannot break completely, but with some information, we can break this system. And for that, I have to discuss lattice. Maybe probably tomorrow we'll discuss lattice and Coppersmith type of idea. So we first discuss RSA public key. Why do we need cryptography at all? We have two friends, Alice and Bob, and Alice wants to send some message to Bob. This is old story, so you know this thing, but somebody always in middle, Eve is here in middle, and Eve tries to get that message. So Alice needs to encrypt her message to Bob. Now, for encryption, there are two ideas. One is symmetric key idea, and another is public key idea. Symmetric key and public key. So in symmetric key, both encryption key and both decryption key both should be same. And again, symmetric key, mainly you can divide into two ideas, two types of design. One is block cipher. Probably Professor Panteleimon-Steniker will discuss block cipher today night. And another idea is stream cipher. And asymmetric key or public key is completely different. Here, encryption key and decryption key should be distinct. They should so from encryption key, but from that encryption key you should not get that corresponding decryption key. So why do we need public key? Because suppose now I am in Germany and you are in, say, in India, and you want to send some message to me. Now in symmetric key, we have to first share that key. So if I am in say in Mumbai, and we can share, we can toss coin, say 128 times, and get 0-1 sequence. It should be completely random. Then we can use block cipher, and so we should share that key 128 that string, that random binary string. Then when I am in Germany, you can use that 128 string to generate some more random looking string using stream cipher and encrypt your message, or maybe you can use that with message and encrypt that message using block cipher and send to me. Since I know that key, I decrypt. But now, since I am not in Mumbai and you want to send some message, so we cannot share that key. We need something different. So public key comes this place, and you can solve this problem using public key. So public key idea here is something like this. So you have basically so basically here C is Alice, and second is Bob, and Alice asks Bob that, hi Bob, give me your public key so that I can encrypt some message. So Bob now gives his public key to Alice. Now using this public key, Alice encrypts, get the ciphertext, and now she sends the ciphertext in insecure channel like normal Gmail, And since Bob knows his decryption key, using that decryption key, he will get back that message, that plain text. So symmetry key is not new. This is basically from before than Julius Caesar, but public key is relatively new. First, this kind of key exchange protocol was due to Diffie and Hellman in 1976, and they got Turing Award for this. Turing Award is kind of topmost award in theoretical computer science. They got Turing Award in 2015, and after that, in 1977, Rivest, first one is Rivest, second is Shamir, and this guy is Edelman. They invented this crypto system, RSA crypto system, and for this invention, they got Turing Award in 2002. So before going RSA crypto system or Diffie-Hellman key exchange, I will first make what is the current situation. In your Gmail, you know that this kind of lock. Now, if you click on this lock, just click, then you will get this kind of message. TLS, ECDHE, RSA with AES 128, GCM, SA 256, like this kind of message. That means first one is this ECDHE means elliptic curve Diffie-Hellman key exchange. So basically, in your Gmail, knowingly or unknowingly, you are using elliptic curve, and using elliptic curve, you exchange your key. Also use RSA crypto system. AES is block cipher, and this SHA-256 is hash function. I am not going this SHA-256 or AES. I will focus only in this part, this RSA crypto system. Okay, so basically these things are not only theoretical, this is basically practical. We are using in our Gmail, in our Facebook, almost everywhere. In any secure communication, we have to do some kind of crypto, and RSA is very common. Although it was invented in 1977, many attacks, but still this is secure and very, very simple. But yeah. Now, there are many public key crypto system. First, already I told you RSA. Another is El-Gamal crypto system. This is another crypto system. And elliptic curve cryptography. That means cryptography based on elliptic curve. It has some advantage. And NTRU and McEllis. So there is perhaps you heard about quantum cryptography, quantum computer. Now, using quantum, still I don't know exact situation there, but if quantum computer is actual make that huge gate, then both RSA, El-Gamal, and elliptic curve all will collapse. So you have to do something different, like NTRU crypto system, which is based on lattice. Lattice seems still secure even in quantum, or McEllis crypto system based on coding theory. So let me first discuss Diffie-Hellman key exchange. This is not public key crypto system. This is key exchange protocol, which was invented around 1976. This idea was very simple and elegant, and but it was open for a long time. Before that, all crypto systems were symmetric key, where both encryption key and both decryption key both are same. But here is slightly different. But how you can exchange your key? Now after this exchange, you can use your symmetric key idea. So here again we have two friends, Alice and Bob, and we have to take one large prime P, and ZP star is cyclic, ZP cyclic group. Take a generator G. Now take some small a. In Alice part, Alice will take small a. She calculates g to the power a modulo p. In Bob's part, Bob will calculate g to the power b modulo p. So capital A equal to g to the power a modulo p and capital B equal to g to the power b modulo p. Now Alice will send Bob this capital A. So Bob knows capital A and Bob will send capital B to Alice. Now Alice knows the small a and she also knows this capital B. Now she just calculates b to the power a modulo p, and in Bob's part, Bob will calculate, since he knows this capital A, Alice already sends her this capital A, and b is known to, the small b is known to her, so he calculates a to the power b modulo p, and it is not difficult that this a to the power b modulo p and b to the power a modulo p both are actually same. Just you can calculate capital K equal to b to the power a modulo p, and b is nothing but g to the power b power a modulo p. Now if you just exchange roll small b and small a, you will get capital A to the power b. Okay, so if you have any doubt, you can ask me till now. So Riemann exchange is okay. We hope so. Now come famous RSA crypto system. So here story is same. We have three friends, Alice, Bob, and somebody in middle, Eve. Now in RSA crypto system, Alice will just send her message to Bob that Bob, give me your public key. I want to send some message to you. Now Bob will generate some large primes. I will tell you why we need large, not small prime, not like 3 or 5 or 7. He has to generate large primes, at least 512 bits, large primes P and Q. Then he calculates N, which is product of P and Q, and Euler phi function, phi n, which is all numbers less than n and prime to n, and in this situation it will be product of P minus 1 and Q minus 1. Then he generates two numbers, E and D, so that this guy, this phi n, should be divisor of ED minus 1. And using extended Euclidean algorithm, this is not difficult. You can easily calculate. So again I am repeating. So Bob has to first calculate these large primes, at least 512 bits, then their product, then Euler phi n, phi function, this product, and P and D, two numbers, so that this phi n is a divisor of ED minus 1. Now he makes this n, this product, and this E public. So just normal public key, normal using say Gmail or just SMS, this N and E. So everyone knows these two numbers, N, this large N, and E. Now message is say M. So instead of sending this M directly to Bob, Alice will first calculate M to the power this E modulo N. So ciphertext C is M to the power E modulo N. Then Alice will send the ciphertext to Bob. And in Bob's part, Bob will calculate this C to the power D modulo N, and it is not difficult to prove that this C to the power D modulo N is actually M. So don't need to send M directly, send this M to the power E modulo N, and Bob has to calculate C to the power D modulo N and get back message M. So this is the idea of RSA crypto system, RSA encryption. So this is kind of padlock. You can lock easily, but to unlock you have to get that key. Similarly, anyone can encrypt from the knowledge of public key N and E. Anyone can encrypt, but to decrypt, you need this D, this number D. Okay. And mathematical, this proof is very simple actually. So I'm not going to the proof. So till now, any doubt? You can write in chat box. I think that is possible. Okay, so these are some small example. If you take prime equal to this and q equal to another prime is this, then product will be this, and phi n in this situation will be this. You can take e equal to 13. You can check 13 times this number is 1 modulo pi n. So decryption exponent d is nothing but this number. Now suppose message is 1, 2, 3, 4, 5. So don't send that message directly. Just calculate this to the power e. E is 13 here. E to the e modulo n. This number. So ciphertext will be this. Okay. So this is actually a very small example. Now so this is one task you have to solve. Very simple. So basically, suppose e equal to 7 and q equal to 11 and e equal to 43, then what's the value of d? You can write chat box and so go back again this slide, maybe this primes n phi n, and phi n should be divisor of ed minus 1. What should be the value? Yeah, so basically this is one question is, if someone knows n and e, then can he calculate d? Now this is still difficult. This is basically open problem kind of thing, but till now there is no efficient algorithm from which, just from knowledge of n, when your n is large enough, and e, you can find d. I will discuss, but if you know p and q, that means if you factor n, then you can easily calculate phi n, which is product of p minus 1 and q minus 1. Then from knowledge of phi n and e, it is not difficult to find d. So if factorization is easy, then you can break RSA. But on the other hand, so this is basically one direction. If factorization is easy, then you can break RSA. But it is not known whether you can break RSA without knowledge of factorization. That is open problem. Basically, no. D is 17. So for this example, what should be the value of D? 17? Is it coming 17? I am not sure. At least in my calculation, it is 7. So maybe I am missing or you are missing. But idea is, so here phi n is 6 times 10, 60. So 7 times 43 modulo 60 should be 1. Okay. Now, if suppose hypertext is 2, then, okay, sorry. What should be the message? Yeah, 7. It is 7, true, great. So suppose hypertext C is 2, then what is message? Not C, this should be M. So what is message? So you have to calculate 2 to the power d modulo n. So in my calculation, it is 51. Maybe you have to check. Okay. So anyhow, so you know the idea. So basically, you have to calculate 2 to the power 7, which is 128 modulo 77. So not modulo phi n, modulo. So just let me back. E to the power d modulo n, not c to the power d modulo phi n, not like that, c to the power d modulo n. Okay, and these are small. This is just toy example, but you cannot do, because if I give you 77, immediately you can factor p 77, 7 times 11. So immediately you can find phi n, and from knowledge of E, you can easily calculate D. So you can easily break that crypto system, break RSA crypto system. Let me again come back. So if you factor n, you can easily calculate phi n, and you know E is public. Then same Euclidean algorithm, the GCD finding algorithm, you know that algorithm. Using that algorithm, from knowledge of phi n and E, you can find D. So whenever you see this hypertext in the middle, you can calculate c to the power d modulo n. N is anyhow public, so you will get back message M. So if you can factor n, you can break RSA immediately. This is simple. So here underlying assumption is you cannot factor. Now if I give you say 15, you can factor 3 times 5, or 77 you can easily factor. So you need something different, something large basically. So this is one practical example. You can take this huge prime 512 bit and another 512 bit, then product of these two numbers will be like this. E take E equal to the power 16 plus 1. This is very common in RSA because of some advantage in encryption. Because if you write this to the power 16 plus 1 in binary, you have only 2 ones, all are middle 0. So that encryption will be faster. And in this situation, D will be like this. So many times, depends upon situation, but many times is taken as this small number 3 or 2 to the power 16 plus 1, and D is large. So for RSA, so you now understand that you have to generate large primes, not like 7 or 11 or 13. You have to generate large primes like 512 bit. Now, how we can generate large primes? One idea is you can take one number and you want to test whether this is prime or not. So you start from 2, 3, like that way, divide up to say square root of that number. If no number divides that number, then this is prime. So if you want to test whether P is prime or not, you start with say 2 divides P, 3 divides P, 5 divides P, like that up to square root P, because if P is not prime, if P is composite, then at least it has one factor which is less or equal to square root P. So this is very simple idea, but we are working with large numbers. So like P is 512 bit. So square root is around 512, around 256 bits. So 2 to the power around 2 to the power 256. You cannot go like this way, because even if you assume that you can calculate say 2 to the power 50 operations per second, you just check how many seconds do you need to check whether some number is prime or not, for practical example. So we cannot do like that. And you know that this formula, Wilson's theorem, that if P is prime, then P minus 1 factorial will be minus 1 mod P, and this is basically two direction. If P is prime, then this is true, and if this is true, then P is prime. But again, you cannot calculate P minus 1 factorial when P is large, big number. So again, for theory it is fine, but to test whether number is prime or not, we cannot use this formula also. But this Fermat's little theorem, this we can use. If you know if P is prime and GCD between A and P is 1, then A to the power P minus 1 will be 1 modulo P. This is Fermat's little theorem. So now, you can take a large number, 512 bit, take a random A, say you can take A equal to 2 or A equal to 4, any number, then calculate A to the power that large number minus 1 and take modulo P. Of course, you cannot just calculate A to the power P minus 1 because P is large enough, and then divide. We have some clever technique, divide and that square and multiply kind of idea, but just assume that we can do this kind of modular exponentiation efficiently. Then using this idea, you can check. But the problem is, there are some numbers like 341, and you know that GCD between 2 and 341 is 1, and 2 to the power 341 minus 1, that means 2 to the power 340 is 1 modulo 341, but 341 is not prime. So this, although Wilson's theorem is both direction, but we cannot use, and this is one direction. In some time we can use, but this is not. So if this is not equal to 1, then definitely this is P is not prime, P is composite. But if this is 1, we cannot tell. We cannot tell that this is prime. This is the problem. And there is concept Carmichael number, like 561 is first Carmichael number. So this kind of numbers, if you take any number A such that GCD between A and 561 is 1, then A to the power 561 minus 1, that means A to the power 560, and if you make modulo 561, it will be 1. So although 561 is not prime, but if you try to use Fermat's little theorem to test whether this is prime or not, it behaves like prime. If you take any number A, and if you, so that GCD between A and that this 561 is 1, then calculate A to the power 560, you will get 1 modulo 561. So this is the problem, and Carmichael number are basically infinite. Yeah, so one question I am seeing that, like this number is large n, is it possible to factor this number using classical computer? Yeah, till now this is very difficult, almost impossible. I will discuss that factorization current state apart. This number is 1024 bit, but till I think I will discuss. Some 850 or something we have. There are some factorization record. I will discuss. Yeah. So there is concept of Carmichael number. So for that we cannot use Fermat's little theorem. We have to do something different. There are some primarity tests. One famous test is Miller-Robin test. Miller-Robin test, if it tells composite, then definitely it is composite. And if it tells prime, then it is prime with some certain probability, 3/4. So you have to run many times, and if each time if you get prime, then probably this is prime. So this is probabilistic test, but almost with one probability, 1 minus some epsilon probability, you can guarantee that whether this is prime or not. And another test is Solvestratian primarity test. I will not discuss this test, but these are not difficult. And one, just notice this Miller-Robin test is deterministic test if we assume that Riemann hypothesis is true. But these are practical, and for all this kind of generation, large prime generation, like here, you have to use Miller-Robin test. But both are probabilistic test. But probability is almost like almost 1 minus some epsilon. And I should tell about AKS test. Agarwal, Coyle, and Saxena. They invented this test, how to test whether a number is prime or not, but this is not probabilistic, this is deterministic. Although Miller-Robin is practical, or Solvestratian, both are practical, but these are not deterministic tests, both are probabilistic tests, and Riemann hypothesis is still hypothesis, so Miller-Robin is not deterministic, but without any hypothesis, they proposed this AKS test, and this is deterministic test. And idea is, suppose x is a variable, a is any number, then x minus a to the power p will be x to the power p minus a modulo p if and only p is prime. Using this idea, you can check whether a number is prime or not with one probability. Not 1 minus epsilon. There is no epsilon here. Epsilon is 0 in this, using this test. This is deterministic test. Okay, so come to factorization. So already I have mentioned that if you factor this number n, then you can easily calculate phi n, and E is public. So you using extended Euclidean algorithm, you can find this d, and whenever you know this d, then from C to M is very simple. From ciphertext to message is just you have to calculate C to the power d modulo n, and you can break immediately. So assumption in RSA crypto system is you cannot factor large number. And now we have RSA crypto system, but famous mathematician Gauss, he realized the importance of factorization, not for only for cryptography. This is actually classical math problem. And there are some factorization algorithms like Pollard's P-1 algorithm, quadratic shape algorithm, early 80s. Then using elliptic curve, you can factor, and using number field. So instead of over integer, you have to go number field, and using that idea, you can factor. But this is 1993. After that, still this is the fastest factorization algorithm. So these are some time complexity, quadratic shape algorithm, and elliptic curve is this complexity, and number field sieve is this complexity. So for small number, when n is like 512 bit, then quadratic sieve is faster to do a 60. No, for small number like 3 84, you can see that this is faster, 2 to the power 55, and but this is 2 to the power 56. But after certain that threshold, number field SIP is better. Like in my example, it was around 1000. It was basically 1024 bit. So for 1024 bit, using quadratic SIP, you need this kind of 2 to the power 98 many time complexity, and number field SIP is 2 to the power 86. Now again, if you assume that you can calculate 2 to the power 40 operations per second, again, so you need 2 to the power 46 seconds to factor this kind of number. So which is huge, you can calculate. And elliptic curve factorization will be faster if your primes are not balanced. One is very small and another is very large. Then in that situation, elliptic curve factorization will be better. But in RSA, primes are almost same size. Same size means you have to choose your P so that P should be more than Q and less than 2Q, this kind of bound. Not like one is 3 and another is say 29. Not like that. Both are almost like 29 and 31 kind of idea. Not. And this is the factorization record. Yeah, so this is last year. We have factorization up to only 829 bits. RSA 250. So now 1024 is far from here. So just using classical computer, it seems that we cannot factor maybe using next 10 years for 1024 bit number. And RSA 250 was this number. It was challenge number organized by RSA company from early 90s, and after 30 years almost, people factored this and they got this number. And one thing I should tell, that if we have quantum computer, then polynomial time factorization, that means we can factor in practical time, is possible in some sense, but till we don't have quantum computer, and it is not clear whether we have within next 10 years. I am not sure. So this is the factorization situation till now. So up to now, do you have any doubt, any query? Then I will go one simple attack on RSA. So in general, although factorization is very difficult, but if we don't use RSA parameters properly, we can factor easily. So just factorization is difficult, but n together with knowledge of encryption exponent E, sometimes you can factor. No, brute force is not possible. So one question is, for RSA 250, are they use brute force or random factorization? No, not random factorization. They use number field SIP. This idea. This 1993 idea. And the implementation is really a big thing in this idea, because you have to now make everything in number field, not over integer. So actual implementation over this thing is a big issue, and there are many issues. They used huge machine, and I think group from USA, France, and Germany all together tried this number for factorization, and finally they cracked. And before that, you can say before that it was 232 bit in 2009. So almost it took 10 years for next factorization. Yeah. So any doubt? Any other question? if you have any question, then it's fine. Otherwise, I will move. That although factorization is difficult, but n together with public exponent e, sometimes factorization is very simple, very easy. So one idea is continued fraction idea. You know this idea. Any rational number you can express like this way. Like 34 by 99 you can write like this way. And we call this is sequence corresponding to this 34 by 99. And convergence. So from this sequence you can get back your original rational number 34 by 99. So for some number a by b, you make some initial sequence, and from this initial sequence you can get corresponding subsequence like 34 by 99. First one number is 1/3 and 1/3 is close to 34 by 99. So using this idea, now one result, this is again old result. If GCD between A and B is 1 and GCD CD is 1, then if, and third condition, if this modulus is less than 1 by 2d squared, then C by D will be one of the convergence of the continued fraction expression of A by B. So from the knowledge of A by B, you can, one option will be C by D if this is less than 1 by 2d squared. Now, why not in 1990 use this theorem, this old theorem, to prove that one can factor n if decryption exponent d is less than n to the power 1/4. 1/3 times. We are working over large numbers, so many times we will not consider this small constant, 1/3 or 1/5 or something. We are so if d is less than n to the power 1/4, then we can factor n easily in polynomial time. So idea is, in RS equation, we have this ed equal to 1 plus k times phi n. So if you expand phi n, you will get this number. Now, e by n minus k by d will be less than 1 by 2d squared whenever your d is less than this. So from the knowledge of e by n, you can find k and k by d, and from k and d you can find phi n, and from knowledge of phi n you can easily get p and q. So if d is less than n to the power 1/4, d is less than 0.25, factorization is easy if you know e. So just n factorization of n is difficult, but if you know n, e, and if corresponding d is less than this, then factorization is easy. So this is that example, one example. So n is this, equal to this. Again, toy example, n is this is not practical n, but again continued fraction will be like this. So few convergence of e by n will be like this. Take each of them and try. For example, you can take k by d equal to half. One is second, first is 0, second is half. You will get phi n, and from this phi n you will have p. This is not integer. Like this way, whenever you reach 14 by 37, k by d equal to 14 by 37, your phi n will be this, and from this you will get primes p and q. So whenever your d is small, into the power 1/4, then factorization is polynomial time. So again, you can consider when your n is say 1000 bit, into the power 1/4 will be around 250 bits. So you cannot just try and guess for each d, but you can use this idea to find that find d. Okay, yeah. So any doubt? So today I think I should finish. If you have any doubt, you can write or call. Okay, so when we say it is polynomial time means it is polynomial in number of bits. So we are working over n. So number of bits means is log n base 2. So if anything is polynomial of log n base 2, or again base is not important because instead of base 2 you can make base e or base 10 because only some constant will come out. So if anything which is polynomial in number of bits or number of digits, we call that is polynomial time. No, RSA is basically working for encryption and decryption. So that is our purpose. We are not trying key exchange. Key exchange, that is slightly different. So basically, RSA is only for one encryption part and another is decryption part. Key exchange, and that is different. We are not discussing here key exchange. So key exchange, defilement key exchange is for 2 people, and there are some idea. Using that idea, you can make key exchange between 3 people, but that is much complicated. Defilement, you can see only defilement only simple, but you can make key exchange for 3 people using elliptic curve. So already you need something more mathematics, and more than 3 is really difficult. There are some researches going on multilinear maps, and still I think difficult. Okay,
there is another question in the chat box by
yeah.
Okay.
How with n and phi n we are calculating p and q in Y0 setup. So if you know phi n, so let me come phi n again. Yeah. So if you know n and if you know phi n, then you can replace q, right? Q will be n by p. So you will have a quadratic equation over integer, and you can easily solve that equation. You have some ax square plus bx plus c kind of equation over integer. You can easily find that root. So if you know phi n and if you know n, you can replace q by n by p and make quadratic equation, and you can solve. Okay. So next question is again polynomial time. So polynomial time, in some sense, you can think like efficiently, or polynomial time formally it is polynomial in size of your input. So you have one algorithm A, your input is say x. If required time complexity is polynomial of log x, then we call that is polynomial time. Like here, you have to check whether number p is prime or not. So p is a 512-bit number. Then if you check whether this is prime or not with complexity of polynomial of 512, then we call that is polynomial time algorithm. No, basically, next question is security increases if difference between P and Q is large. No, so basically, P and Q should not be very small. The difference between P and Q should not be very small. In fact, if P minus Q is less than n to the power 1/4, then you can factor n easily. On the other hand, so there is one idea. On the other hand, if P is very small and Q is very large, then using elliptic curve algorithm, elliptic curve method can factor. So P and Q should be kind of balanced. So So like n equal to 1020, if n is 1024 bit, then both P and Q should be around 512 bit. But one not like one is 100 bit and another is 912 bit, 924 bit, not like that. Then in that situation, one can use elliptic curve to factor that number. So both should be almost like log n by 2. Whether it is easy to find P and Q by knowing only phi n. Yeah, this is basically easy, right? Because anyhow n is public, and if we know phi n, you can make it quadratic equation over P and you can solve. No, so basically if difference is really big, then using elliptic curve you can factor. So difference should not be, so I can come elliptic curve and complexity. Yeah, so you can see elliptic curve time complexity is square root 2 log q log q. Now if, and this q is smaller factor, if q is much smaller, then this will be very small, so you can factor. So both should be almost same size, not like one is very large and another is very small. Not like so suppose our n is 1000 bit, not like one is 900 bit and another is 100 bit. Both should be around 500 bit. So that then this is the most difficult part. On the other hand, if both are 500 bit and their difference is not big, then again using lattice idea, tomorrow I will discuss lattice idea, you can factor. So choice is really important. Like your prime should be this polar p minus 1 algorithm. Your prime should be such that all prime factors of p minus 1 should not be small. At least one should be large. If I mean, suppose all factors are some 2 to the power 10, 3 to the power 20, 5 to the power 30, like that, then one can factor. So all prime factors of p minus 1 should not be small. One should be large enough. Otherwise, using Pollard's p minus 1 idea, one can factor. Yeah, any doubt?
I think in chat box there are no more questions.
Yeah.
So, yeah. So if there are more questions, either you can write in the chat box or you can unmute yourself and you can ask directly. So there are some comments. Thank you for a wonderful lecture on RSC. There are several comments. Yeah.
Thank you.
It seems there are no more questions. So thank you, Santanu, for your wonderful talk. And,
thank you,
yeah, let's thank him once again.
Okay.
Okay.
Okay, bye.
Okay, have a good day.
Thank you.
Thank you, Santanu. So next talk is scheduled at, let me check, at 8 o'clock in Indian Standard Time.
Yeah.
That is by Panteleimon Stanica on block cipher. So there is a break of half an hour. So we'll reassemble again at 8 o'clock.
Thank you. Hi, Pante.
Good morning.
Yeah, good morning.
Or good evening at your place.
Here, but yeah. So, you're a morning person, huh?
No, I'm not.
No, you're not? Okay. Okay, welcome to the club.
Well, given the fact that in the past year we haven't really been going to the office, we taught at home, and
Right.
this is my home office here.
Yeah.
So I didn't have to wake up that early, just to drive to school. I'm about 5 to 10 minutes away from school, which is great.
Okay.
But yeah, so fortunately, I haven't actually taught except for last summer. I'm on sabbatical until July.
Okay.
Unfortunately, couldn't travel, but
Yeah. That's a pity, actually.
Yeah.
Sabbaticals are a good period to travel.
Yeah, well, not this year.
Not this year.
But maybe I'll have some possibility of actually traveling in 1.5 months or so.
Okay.
So
sounds good. Did you get your vaccine?
I'll get the first dose on Thursday.
Okay.
I'm scheduled. Hopefully they won't cancel it, but and then 20 days after the second, and then
We should be good to go, huh?
Yes, absolutely. Give me a second. Sorry.
Yeah. Yeah, we still have about 4 minutes. Sartaj is there.
Hello, Pante. Good morning. Yeah. Yeah, so we still have 2 minutes to go.
Just trying to see if my slides are shared.
Yeah.
Yeah.
Do they scroll?
They scroll. Can you enlarge them further? I mean, oh yeah. Yeah, that's
maybe.
So there's one indication that your talk was prepared 1 month ago, I think. Because this is no longer at the Rashtriya Raksha University.
Ah. You mean things have changed in a month?
Yeah, they did.
Wow.
They did. Yeah. So I will tell you the story some other time.
Sure, of course. There was a comment in a chat, but
Oh, yeah.
I will send you some books on history cryptography, and then you can share it with one of the members of the audience. I just got a comment on that.
Okay.
I think it's about to, yeah.
Yeah, it's just about.
So should I start or?
Yeah, please. I think you can. Yeah. Maybe.
Okay. So welcome to my second talk of the conference. I will go over some block cipher overview, modes of operation, designs, and two major ciphers, namely data encryption standard and advanced encryption standard. A little bit of history. The whole business actually got started in the, of course, unclassified community around in the beginning of the 1970s. So at the time, U.S. National Bureau of Standards, NBS, now NIST, National Institute of Technology, they issued a call for a strong encryption primitive to become a government-wide standard. Of course, the major players were big companies like IBM, and they submitted, actually in the second call in 1974, they submitted a modified version of their cipher Lucifer, which was designed actually prior to that in 71. Among the proposals, the members of the committee actually, UBS, of course, NBS chose Lucifer, but a modified version of Lucifer, surely because he wanted to be sufficiently flexible and implementable in the day's actually computational power. So there was a year of intense collaboration between IBM and NSA, and data encryption standard was born and published actually in 75 in the Federal Register. Every standard nowadays in the US is published in Federal Register. Now, there was obviously some controversy at the time because Lucifer used a key of length 128 bits, but data encryption DES used 56 bits. So why was it shortened? I mean, people have wondered. And of course, U.S. Senate actually got involved and they investigated the matter. And the conclusion was that the old design principles and decisions were made by IBM developers, although even in that case, there was some controversy. NSA did not tamper with the design of the algorithm in any way. IBM invented the design of the algorithm, made all the pertinent decisions regarding it, and concurred that the agreed upon key size was more than adequate for all commercial applications for which this was intended. One thing that I have to mention is this was actually intended to be used for about 10, 15 years, right, as a standard. Well, actually made it for a lot longer than that, as I will mention later. Now, it was approved, as I mentioned. It was published and approved as a federal standard a year after, 76, republished as a standard 83, 88, and in 98 was modified in triple DES. I'll mention what the triple DES is later on. I probably should also mention that, of course, a very standard, the exhaustive key search would be the only efficient attack on DES. In about 1990, Eli Biam and Adi Shamir discovered differential cryptanalysis, although discovered the unclassified community because apparently the IBM developers we knew about the differential cryptanalysis, and DES was designed to be resistant to differential cryptanalysis. Of course, linear cryptanalysis was also discovered by Mitsuru Matsui, again unclassified, and unfortunately, DES was actually not prone to the attack on linear cryptanalysis because it requires 2 to the power 43 known plaintext, which is really unfeasible, 2 to the power 43. Now, in 2002, of course, years before that, NIST issued a call for a replacement for DES. NIST actually adopted the advanced encryption standard, and I will go through those shortly. Now, for a standard to be approved, you have to have some minimum acceptability criteria, right? So it has to be symmetric, remember, knowledge about the key, the encryption key reveals the decryption key, and vice versa. The algorithm must be a block cipher to have diffusion confusion, and the algorithm must be capable of supporting key block sizes combinations of 128-bit keys, 128-bit block sizes, 192 keys, 256-bit keys, 128-bit block sizes. Of course, you can shorten, you can pad it, and there are modifications of AES even for commercial applications, bank cards, and things like this, where you use a truncated, actually, advanced encryption standard. Now, for AES, there were, we know a lot more for that, of course. It was a lot more public than for DES. I was too young for DES. Now, there were 5 finalists actually for the advanced encryption standard: MARS, which was proposed by IBM; RC6, which was proposed by RCA Laboratories. Ron Rivers actually was one of the promoters there. Rhindale, which was proposed by John Damon and Vincent Ryman; Serpent by Anderson, Beam, and Newson; and Toolfish by Bruce Schneier and well-known cryptographer, cryptologist, and his team at the time of Counterpane Systems. Now he moved. Okay? So let's get the show on the road and say exactly what the block cipher is. So a block cipher, it obviously acts on a plaintext, which is divided into separate blocks, right? Of whatever size, 32, 50, whatever. It doesn't matter what, it does matter for that particular standard, but it doesn't matter what the size is for the design, right? You will see later on that people like to work in a variety of algebraic actually environments. So of course, you split up your block into sizes that actually allow you to work in those environments. So sometimes we work with bits, sometimes we work with bytes, right? 8 bits blocks or strings. Ultimately, mathematically, block cipher is a pair function that acts on some vector space of dimension n over the two element field, right? So basically, it takes a key and a plaintext and maps it into a plaintext of whatever size, let's say m. So the key is of size. Of course, the decryption function does the same thing. It takes a key, well, the inverse key, if you will. It takes the ciphertext and it maps it into the plaintext. So mathematically, it's very simple. Well, obviously vague, but very simple to describe. Surely, the key space is the set of all keys where k is allowed to be in for good implementation, surely. And the decryption function is the inverse function for the encryption, okay? So that's, again, the lowdown on the mathematics. Now, I mentioned to you that you take your plaintext, which is not necessarily divisible by whatever the n is, and then you pad it using some padding techniques that are well known, and then you basically encrypt each block. Now, how do you actually encrypt that sequence of blocks? Well, you have various modes of operations, and I'm going to go through those methods actually now, some of the adopted and well-known method, modes of operation, and the design principle for each block. So I'll do first, how do you manage the entire plaintext or the sequence of blocks, and then I'll concentrate on a single block and on for some ciphers. The block ciphers method actually use usually an iterated block cipher method, which is basically you do a single block independently from the other, or you merge them in some way. Again, I'll show you some of the merging techniques. And you do use some simple operations, sufficiently simple to be able to implement them. Remember that one of the criteria was flexibility. So you have to be able to implement it easily. Of course, some of the people who implement them are not, experts in mathematics, so you cannot give them, too heavy duty, actually, mathematics or computer science for that matter, in the design. So they have to be able to implement them easily. So you'll see sometimes we actually give various ways of implementing a certain function as a lookup table, as a mathematical function for people like us. Okay. Now, the modes of operations, I mentioned to you, I'm not concentrating now on a single block. I'm concentrating how do you encrypt the entire sequence of blocks. Well, you have the ECB, which is the electronic codebook mode, is the simplest mode out there, and I will have a picture later on. Basically, what you do is you partition the plaintext, the message, into several blocks, and you do independently the work on each one of them. Surely you pad it if necessary, and you apply the ciphertext to each block independently. There are advantages and disadvantages, surely. The advantage is that you can encrypt and decrypt the blocks actually independently. So you can do parallel work. The errors do not propagate. So if you make an error in a certain block, it doesn't propagate in a different block. Well, the problem is the disadvantage is that this mode does not hide data pattern. So you see your blocks may have the same pattern somewhere. And if you reuse some of the keys, for instance, in different blocks, you will see that pattern popping up. There are obviously some, you can look on, I don't know, Wikipedia or some other places, some of the, like a Penguin encryption, for instance, using the ECB mode. Of course, the Penguin has different portions of its body black, and of course, those will actually be revealed if you use, just a few rounds ECB mode, because black, regardless of, not regardless of what the key is, but it doesn't actually change much, right? So you will see some of the pattern popping up in ECB mode. So this is basically the lowdown, the picture that tells 1,000 words. They're trying to call ECB mode. You take the plaintext, you apply the key, you encrypt it, and you do this independently from the other ones. Well, what else can we do? Well, we have also cipher blockchaining mode, which encrypts the first block using the ECB method, and then apply the XOR the first block with the block IV. So again, I probably should show you the picture. This is actually the picture that tells the whole story. So you see the first block is done in the ECB mode. Now, the output of the encryption of the first block is used basically to XOR, to one-time pad it. I didn't have the time yesterday because I wanted to finish before the clock, but the one-time pad is the only provably secure cipher if the key is not reused, okay? Because it's done bitwise. I mean, you add up the plaintext, the key as long as the message, so you don't actually reuse or you don't use any mode operation there. You just add up bitwise, and of course you have 50% chance of guessing what that bit was. That's not possible. Again, you cannot reuse the key. So it's the only proof of security. You will see the one-time pad occurring in basically almost every cipher out there, in some form or another. So it's just a very simple and nice and very fast operation, but you have to be careful, okay? Now, again, I'm using the output of the previous ciphertext block as an IV. I'm XORing, I'm one-time padded the plaintext, and now I'm feeding it into encryption machine. And the same thing here. So the output of the ciphertext here is used as an IV. IV stands for initialization vector, and that's the cipher CBC. So the cipher blockchaining method. What else can we do? You see, at this point, knowing the two modes of operation, the first two modes of operation, you can come up with your own mode of operation. And that's exactly you will see later on. What else can we do? Well, we can do output feedback mode. So it avoids error propagation, no rekeying, of course, but uses the output of the encryption function as a feedback, as an IV, right? So ultimately, what you do is the plaintext is, again, one-time padded with an output feedback. That's my ciphertext. And the output feedback actually is encrypted via the key. So you see, I'm not encrypting the plaintext or the sum between the plaintext and IV. I'm encrypting the output. The output. So it's not the plaintext necessarily. The plaintext is simply one-time padded to the output. So the picture again, you have an IV for the first block. You encrypt it. You XOR it, the plaintext. You spit out the cipher, right? And now this actually is used as an IV. So the encryption of the output, the previous output, is used as an IV for the next block. Okay, for the next block. No error propagation in the encryption of the plaintext, which is the one-time pattern, right? Because you don't use that. So that's the output feedback mode, the OFB mode. Again, a nice picture that tells the entire story. So what else can we do? Well, we use basically in the previous one, we use the output of the ciphertext here. We use here the output of the encryption. What else can we do? We're the cipher feedback. So what you do is you take the output of you encrypt the ciphertext, the previous ciphertext, and now you one-time pad it the plaintext, and you use that as an IV, you see? every single the IV for the next encryption is actually the encryption of the ciphertext. So I use here, I use here, I use here, I use the output here as a feedback for the next one. That's the CFB mode. Well, there are actually some other ones. One of them is the CTR mode. These are actually the main 5 that are published by NIST, by the US standards. There's several more that are newer and slightly more complicated. The counter mode is almost like the first one, the electronic codebook mode, but is done independently, so you can do it in parallel, but it's not done only on the plain text. It's done actually on an IV that is rather either fixed, is generated from a fixed one, so it's the initial IV, which is shifted by I modulo 2 to the power n for some n, okay? So every single IV for the second block and beyond is basically based upon the previous one where you modify slightly. So this is again a modified ECB mode. It's called counter mode. Of course, any counter could be used if you have a nice and easy way to generate this particular counter. Randomly or whatever the method may be. So this is actually nice to have if you want to do it in parallel. If you have you can use as many processors as you want. So this is these are the main modes of operation for encrypting a sequence of blocks. Now I'm gonna concentrate on a single block and concentrate on the design approaches for a block cipher. Okay. So general block ciphers, they combine various simple operations, and I'm going to go at the end, hopefully I'll get there, at the end of my talk, through some of the alternatives to DES and AES. And they combine transposition, transformations, arithmetic operations, simple enough that we can actually investigate them. 2 main ways actually to achieve that: Feistel schemes and SPN, substitution permutation networks. What is the Feistel? So Feistel ciphers basically is the basis of the first advanced encryption standard, the data encryption standard, and SPN is the basis of the next one, advanced encryption standard. So these are the main ones. What is the Feistel scheme? Well, it bears the name of one of the IBM cryptographers, Horst Feistel. It is, of course, an iterated block cipher. And here's how it does, basically. Of course, I have the mathematics there, but it's simple enough that I can explain in words. So I have my plain text block of whatever size, right? I chop it up in 2. And then I'm operating on the left and right side of the cipher. So the right side goes unchanged in the next round. So again, I have one single block, not multiple blocks for my plain text, just a single block of whatever size. Okay? In AES in DES is actually 64 bits. So I take 32 bits, right side, I move it to the left-hand side the next round, and the left side is actually, messed up with the encryption of the right side to reveal the next right side. Let me repeat this. So the previous right side is moved unchanged in the next round, and it is also encrypted and XORed one-type padded to the left side to reveal the next right side. So you see, it's interpursed. Is doing this. Now you may say, well, hold on a second, but one of the sides of your plain text is actually left in clear, right, in the next round. Yes, but you do this many times, which means that every even number of rounds, every side is actually gets to be encrypted. So as you can imagine, you will see that the number of rounds is, for many of these ciphers, is an even number for this particular reason. Okay. Of course, the encryption is done basically doing the opposite way. So the left side is actually changed, is basically recovered in clear for the previous right side, and so on and so forth. The decryption function, the encryption function here should have been for the left side actually is combined with the right side to reveal the previous left side. So this is basically what happens. Now there are approaches. For instance, Skipjack, which was one of the NSA's actually ciphers, was declassified in '98. Uses Feistel scheme, but actually in 2 strings of non-equal size. So you may say, well, hold on a second, but once you move it, how do you do it? Well, you expand it. There are expansion methods. You will see some of them actually even DES So although you may have fewer bits, you expand it via some methods to get the right size. You see these expansion methods in many of the ciphers, like parity bits and parity, bits in every byte to be able to have some control on the error correction. Okay, so this is unbalanced. So this is again the picture that tells the entire story. You have your plain text left side, right side. The right side, you see, it moves unchanged in the next round, but it also gets encrypted and XORed to the left side, and that's moving in the next round, the right side, and it keeps on doing this up until for some certain number of rounds. So this is again the Feistel scheme. Now the SPN is different. The SPN is, as the name suggests, substation permutation networks. It is a product cipher in the sense that it involves a certain number of transformations. So every round function is composed of a number of steps that are, of course, combining invertible functions, substitutions, S-box, and permutations. I probably should say a couple of words about the S-boxes. S-boxes obviously stands for substitution boxes, sometimes called lookup tables. And you will see why, because again, they come, although they have a mathematical structure, they come with the lookup table that we can literally look up in a table and say, okay, so this is how the function acts. And I'll show you how to read such tables later on. Again, you have the substitution that does the confusion, and then you have a diffusion process, and then you keep on doing this for a certain number of rounds. Of course, the keys are not all independent. I should have mentioned that for this as well. You have an initial key for the cipher, and that key goes through a key scheduling algorithm. So in parallel, once you do the number of rounds, if I need the key in a certain step, the initial key gets generated, gets transformed via key scheduling, which is published, by the way, and it reveals another key for that particular step. So that's the picture again for SPN. Again, the permutation layers are linear transformations that act on the entire block. They generate diffusion, and the substitution layers, the S-boxes, actually do generate confusion via Shannon. Of course, they have to satisfy a bunch of properties for people working in our area in Boolean functions, vectorial or bit, doesn't matter. They have to satisfy various properties to counter some attacks, known attacks on block ciphers. They have to be highly nonlinear to counter the linear cryptanalysis, correlation immune. There is and this is not only for block cipher, but straight cipher as well, which is not the object of my talk, but the avalanche features and so on and so forth. So basically, they have to have a bunch of properties to counter some known attacks. Okay. Unfortunately, we cannot satisfy all of these at once. So what we do, we have to have a balance. So we have to have the balance sufficiently strong for or sufficiently high, any of these properties for those boxes. We do the best that we can, of course. Now, I mentioned to you that the boxes are Boolean functions. Well, mathematically, a Boolean function, vectorial, mind you, is simply a function that takes an input bit, m input bits, and maps it into n input bits. Okay, so it takes a tuple of m bits and maps it into a tuple of n bits. That's a vectorial Boolean function. Every component of those is a classical Boolean function where the output is a bit, right? So every vectorial is basically a bunch of bit Boolean functions. Now let's go and get our hands a little bit dirty on data encryption standard. So this enciphers a 64-bit data block, again, Feistel scheme. So what you do is you have an initial permutation that takes your plaintext and, shuffles that a little bit. That's an IP. It's called initial permutation. Again, it's fixed. It doesn't change. Well, surely the plaintext changes, but the IP doesn't change. And you only have 16 rounds of a complex key-dependent calculation function. And of course, the final permutation, which is the inverse function for the IP. Now, there are a bunch of criteria that were used in the 70s to generate the boxes for DES. And the IBM implementers and the contractors actually chose 8 of them. Again, there were 1,000 choices, but they chose 8 of them that they felt like they satisfy to the most the criteria. Of course, each row of the boxes, and I'll display them to you next, is a permutation of 0 to 16. Okay, 0 to 15, sorry, 16 entries I meant. S boxes must be nonlinear Boolean functions. Just for fun, you can ask your master's students or beginning PhD students to do some computations on the boxes of this, and not only on AES as well, to see properties of the functions, underlying functions, crypto properties of them, just to see if some newer actually attacks on block ciphers were known in the 70s or 20 years ago, and they were actually made resistant to some of these. Now, the avalanche features, what's interesting about this is on the classified community, the avalanche features were invented in 1985 by Webster and Tavares. Strict avalanche criterion and global actually even later. But the boxes in DES in the 70s were actually chosen to satisfy some of these avalanche features. So for instance, changing one input bit to an S box results in changing at least 2 output bits. Surely nowadays we would like to have, about half of them should change, half of them should not change. So I always say, every change should generate an avalanche in the output, but not too much avalanche. That's actually a bias. Okay, just actually a bias. And they were chosen to minimize the imbalance of any S-box output when any single input bit is fixed. So again, you probably will detect the immunity for some of these Boolean functions in this particular property. But again, that's a different lecture on crypto Boolean functions. Now, this requires about 2 to the power 55. Of course, the key is 56 bits, but on average, we say about half of it, right? Unless you're the unluckiest person in the world to try all the 2 to the power 56 keys, and the last one is the right one. But on average, you try about half the key space, right? So required 2 to the power 55. Of course, this was even nowadays almost infeasible for small companies, not infeasible for a specifically designed computer. DM Shamir actually method used 2 to the power 47 chosen plaintext, and Winner actually Mike wrote a paper. You can download it online. It's interesting. It's a large paper, initial 94 and 98 revised, where he actually made the case for the design of a DES cracker, basically a computer that is designed to crack DES. And at the time, it was initially 94. It was about $10 million to design it, to build it. But it became 1 million, and later on, actually, they produced it. So EFF, Electronic Frontier Foundation, actually put up the money, not even that much, actually, just a few years later, to design the DES cracker. And ultimately, nowadays, we can we can break DES in just a few hours. So again, it operates on a 56-bit key sizes and 64-bit plaintext key. Now, again, 56 bits keys are expanded to 64. You'll see how, because 56 is divisible by 8. You have 8 7-bit blocks, if you will, but each 7 bits will be inserted. To each 7 bits, you will insert a parity bit to make it an odd parity for, and basically the 8 7-bit blocks will be transformed into 8 8-bit blocks. So 8 bytes, ultimately. Each of the 16 rounds of DES use a 48-bit subkeys, which is again produced by a key scheduling algorithm, which was published. So DES operates in ECB mode, but you can do CBC or CFB modes just to combine those sequence of blocks there. So here's actually how it's doing that. Again, that's the picture that I even used in my book. So you have the input, you apply the IP, the initial permutation I'm going to display. You have at every single round, the 16 rounds there, you chop off your block into 2 pieces, and the right side moved unchanged into the left side, as you see, next left side, but is also encrypted and XORed to the left side and moved into the next right side. And you keep on doing this, interspersed operation. Of course, you concatenate that should have been 15, but and you apply the initial permutation to the output there. So that's basically DES and many of the Feisel schemes there. Of course, the number of rounds may change, but the idea behind that, not. So here's actually the initial permutation and its inverse. Now, here's how we read these blocks. Of course, I had to be very careful when I transcribe the numbers there so that I have them all correct. So here's how we read them. Let's say 54, which is right here. Let me see if I can increase the size here. So this 54 is the intersection of the row 17 and column 1. So what we do is, again, that's why it's called lookup table. What we do is we sum up 17 plus 1, that's 18, and 54 will be replaced by 18. So if I'm applying the IP or inverse or S-box, this is how we look it up, how anybody actually without any knowledge of mathematics, ultimately just realizing what numbers are, can look it up and see how the function acts. Okay, how the function acts. So that's basically how we do it, and I say it in here as well. So 54 will be divided by 18 and we apply that particular operation. Okay. Now the core function, again, the entire structure of DES and many of these ciphers relies on the strength of a single core operation, S boxes or S box. In this case, several, but in AES, a single S box actually is the one that gives the security of it. So it consists of 4 operations, the actual core function. The expansion, the 32 bits are actually expanded to 48 by using some expansion, and the expansion actually, again, it was published initially. So you take 32 bits, and then you expand to 48. You mix it up, basically just one-time padded. You, again, remember that the initial key is expanded, is actually not expanded, it's the intermediate keys in each round are 48 bits. So the key scheduler actually reveals that every single round, a 48-bit key that I can XOR the key missing. So it's one-time padded. That's my encryption, basically, with a key. And then you substitute using the S boxes that I have actually, it's 6-bit words that are split up into, and they are fed into the 8 boxes that were chosen initially. Okay, so I'll show you a toy example afterwards on the expanded. And then, of course, you permute it. So again, using the P box and the inverse there. So here's the expansion function. Again, this is what goes in. So from here, actually, in this square here, is what goes in, or rectangle. What goes in, and the sum of the two, row and column is what goes out to expand it to 48 bits. That's the expansion function. This is the permutation that is added at the end. Again, it's just a permutation to shuffle up a little bit, diffusion, the output of every round. Here are the S boxes. I've done quite a bit of analysis on the S box of DES from a variety of perspectives, even graph theory, eigenvalues and eigenvectors and all properties. And I asked some of my master students to have fun with these and even visualize them. I probably should have shown you a picture of one of the boxes in some respect using calligraphs. But it doesn't matter. So again, these are the boxes. Again, every row is a permutation, and the boxes, all of them are vectorial Boolean functions, and they satisfy, good properties. Again, they were invented, they were chosen in the 70s to the best of their abilities, and they resisted longer than they, initially suspected. Okay, more than 20 years, for God's sake. And I am sure and certain actually that triple DES is still used in many corners of the world, and even talking to Visa International people, they even their system have to be back compatible to correspond to banks in remote parts of the world. So triple DES is still used. I'm pretty certain of that. Anyway, so these are the 8 S boxes. So here's a toy examples to show you how easy it is to describe DES. Basically, once you have those boxes sitting on a desk, you can use them. So let's assume I have my 32 bits that were expanded using that first box to the sequence of bits. Now, again, 48 bits is divisible by 8, so I'm going to split it up into 6 bits. Remember that I have to feed these guys into 8 S boxes. So I will have 8 6-bit blocks. They are labeled B1 to B8. I'm going to show them to you. So this is the first 6 bit, is right here, and the next, and the next, and so on and so forth. So these are the 8 6-bit blocks. Now they are fed into the boxes. Now, how are they fed? Well, remember the boxes actually have 4 rows and 16 columns, right? So what I'm going to do is I'm going to take the first bit and the last bit, and those are the 2 bits that correspond to my rows, and the middle 4 bits are corresponding to my column. So again, the first and the last is 0, 0. The middle bits are 1, 1, 1, 0. That's going to be my column. So 0 and 14, I'm looking it up in the table. If I'm looking at again, 0, 14. If I go back to my first box, 0 and 14, if I can find it, 0 and 14 intersect at 0. That's the output of my first box. That's exactly the output of my first box. This is what spits out. And you keep on doing this. The second block is this guy, 1, 0, 0, 1, 0, 1. I'm taking the first and the last. That's going to be the row. I'm taking the middle ones. That's going to be my column. They correspond to 3 and 2. Remember that 1, 1 is 2 plus 1, right? So it's 3. This is 2. 3, 2. If you're looking at the second lookup table or S box, the intersection of 3 and 2 is 10, which is 1, 0, 1, 0. Again, this is in decimal and this is in binary. I hope you quickly realize that. And we keep on doing this for the 8 S boxes. And that's basically the concatenation of all of these guys are basically my output. So this is my output, and this is you apply the P box that is again a lookup table there, and that's the spit out of every round. That's how simple it is to describe this. I think it's amazing to me how beautiful this thing is. Anyway, let's keep on doing this. This key space, the entire one is 2 to the power 56, a large number. Of course, the EFF in 19, they built a special purpose machine with a cost of $250,000 that was able to search 88 billion keys per second. And they were able to decrypt it in 3 days, actually. The time nowadays, maybe, a few hours. The triple DES, which is an iterated DES with 2 or 3 56-bit keys, of course, this jumps up the key space to double. That means 2 to the power 112 or more than that. And the reason for it, you can use this reasoning for first year graduate students when they ask, well, what is the algebra used for? Abstract algebra used for? Well, there are many uses, of course. But what's interesting is that DES is not a group. That means that applying this twice is not actually equivalent to apply this once. Just because if you multiply 2 elements of a group, you get an element of a group. But this is not a group, so that's why the key space actually size increases. Now, again, I don't care what the controversy is when DES came into existence. It has been a great cipher, and it allows us in the unclassified community to work on things mathematical or otherwise, notions that have some uses in cryptography. Now, since time passes, I will go on to the advanced encryption standard. It is an SPN cipher. It was invented by Damon and Ryman, and there are various actually pronunciation, Rindal and Reindal or Rindal, and whatever the case may be. Personally, I pronounce it Rindal. It supports various key sizes, multiples of 32, and keys between 128 and 256. Again, multiples of 32, but the standard actually has 120-bit block sizes, and the key is 128, 192, or 256. Even your phones obviously have the capability nowadays of encrypting 256-bit keys. So the time Android actually was able to make a choice, and even now you can make a choice on the key size, and I think iPhones had by default 256 bits. But again, 128 is just quite secure for normal operations, but 256 for top secret is recommended. Anyway, so the operations on AES, and you will see that I go back and forth from the finite field to the vector space quite easily and smoothly. They're not isomorphic, they're not the same algebraic structures, but they are equivalent in some way. They are, some operations actually can be done quicker on the finite field as opposed to vector space. Some operations are done quicker on the vector space, like matrix multiplication and such. So they work on bytes. Byte level, again, sum is binary sum, the component-wise sum. Multiplication is done basically by multiplying as polynomials in reduced modulo a fixed polynomial, x to the power 8 plus x to the power 4 plus x cubed plus x plus 1. It is reducible, not primitive, mind you, it is reducible. Some people wonder why it's only reducible. You have obviously the structure of the field is satisfy the Zec table, the shift and add pairs, if you use a primitive polynomial, but this was one of the choices. They're more reducible than primitive, of course. AES acts on a 4x4 matrix, so you see already popping up the vector space structure in it. And the entries in this 4x4 matrix is the state. Okay, so each column is called a word and is basically put in as coefficients of a polynomial, cubic polynomial, mind you, because you have 4 coefficients there, and the multiplication of these cubic polynomials is carried out more modulo yet another relevant polynomial to Reindel, which is x to the power 4 plus 1, is not primitive nor reducible, mind you. But the criteria that went to design of Reindel were resistance against all node attack and speed and code compactness on a wide range of platform and the simplicity of the design. It is really, there is a simple single operation actually that gives the security of AES or Reindel for that matter. So it's really very, very simple. I'm not saying that all the other candidates were not secure. Mind you, some of them probably are even more in some sense, but they were slightly more complicated. And the design, I mean, the adopters actually chose AES because it was sufficiently simple and achieved the right security. So therefore, different transformation in each round. So the number of rounds is 10, 12, or 14, depending upon the key size, right? So 10 for the lowest size, 12 for 192-bit size, and 14 for 256 bits, right? So the 4 transformations are sub-bytes, shift row, mixed column, and add round key. Again, you will see again the one-time pad popping in here. Last step, no mixed columns. It made no sense because you can already recover that. The mixed column operation is already known. So if you recover the ciphertext, you can apply the mixed column inverse. Of course, you can undo what mixed column has done in the last round. So it made no sense to use it, but that's about it. Okay. The brute force actually takes about 3.4 times 10 to the power 38 possible 128-bit keys. For 192 is more than 10 to the power 57. For 256, more than 10 to the power 77. Again, just to put it in perspective, this is almost the estimated number of particles in the universe, which is slightly more than 10 to the power 82 particles. So it's really a gigantic number. It's not possible to go brute force. You have to be smart than that. So it takes, for instance, even if you check 2 to the power 55, which is basically the average key space for DES, you should still need 149 trillion years for 128-bit keys to check it, right? So let me show you a picture that gives you a glimpse into each round on AES. So you apply the by sub again, that substitution box, which is again the only nonlinear, strictly nonlinear feature in AES. You shift the rows according to a fixed method. You mix a column, again, fixed method. You add the round key at the end there, and you spit out. So you do this 10, 12, 14 times. Okay, this is for each block. What is the byte sub or the sub byte? Well, that's simply the inverse function combined, literally the inverse function on f sub 2 to the power 8, which is the finite field of dimension 8 over the binary field. And you apply a linear transformation, an affine transformation to it. Literally, this is fixed. So this is the affine transformation, and you combine this function to it. Of course, I can describe the function via the algebraic way or as a lookup table, and I'm going to show it to you next. This is basically the box in hex. So the box, the ASX box, again, we read in the same way as I mentioned earlier to you. And its inverse is also described nicely. Okay. Again, surely you may wonder, well, how come the inverse is not the same as the box itself? Because the inverse of the inverse is the inverse itself. This is idempotent, right? So it's its own inverse. Well, it is not the same because you combine it with the affine transformation. So that changes things a little bit. All right, now, so here are the shift rows and the columns. What's interesting, as I mentioned to you, the state of the AES is operates on a 4x4. In each entry is a byte, right? So the first row stays unchanged. The second row is basically rotated by 1, rotation symmetry, right? It rotates by 1 for people who work in the area. The third row is rotated by 2, and the fourth row is rotated by 3. So the first row stays unchanged, the second by 1, the third by 2, and the fourth by 3. The column is again is done component-wise. Is done on a fixed matrix. Is simply the mixed column is simply a matrix multiplication on each. You see, these are the columns, right? So let's say it takes S3C, which is here. Well, whatever the column is, right? And S2C, S1C, S0C, and it multiplied by this fixed matrix, and it spits out the output in the next round. So basically, you mix the column according to a fixed matrix. Of course, I can also describe using the finite field operation. I just didn't want to do more on this. I hope I convinced you that we move back and forth from the vector space to the finite field. Some things are easy in the finite field, some things are easy in the vector space. They are, as vector spaces, they are isomorphic, but not as, only as fields. I mean, the vector space is not, f sub 2 to the power n is not a finite field. Anyway, so the all-round key, again, acts individually at the word column by adding the round key. Literally, again, one-time padded. So that's the global key, the global actually view on the shift rows. So now going to the mathematical structure, of course, this was done along the way initially. In the initial actually proposal, it was done, but there was also work later on. Damon and Raymond actually they published a book on AES later on, and there were other works to deal with various representations of AES and embedding of AES into other structures, hoping that the embedding actually allows you to have more attacks or attacks on AES. The byte, the sub-byte, basically the composition between the inverse function and the transformation can be also described as a polynomial where the coefficients are in f sub 2 to the power 8, surely. So now the shift rows are clear, and the mixed columns basically are put as coefficients in this modulo x to the power 4 plus 1. So you can also describe it in the finite field. The all-round key is quite clear. Again, Reindel used the CBC and ECB modes by default, the first two, as I mentioned to you. But you can extend to other modes for whatever purpose, CFB, OFB, OSCB, and counter mode. So now, one of the first things that we do, again, very vague, but we do in crypto courses is say that every single cipher basically can be represented as a system of polynomial equations in some way. Of course, every block cipher has been represented as such system. Unfortunately, these systems are so gigantic in size and the number of unknowns and equations that it's infeasible. We don't have a method to do. That's why we call it linear algebra, and not call it non-linear algebra, because we only have methods to deal with linear systems. And sometimes even linear systems fail to be solved if the size is too large, of course. We can represent it in a variety of ways. For instance, it was done a while back that one round Reindel actually satisfies a continuous fraction expansion in somewhere. I probably should just give you this one because it gives you a glimpse into the world. So even after 5 rounds, I can represent the output of 5 rounds as a continuous fraction in some sense. The constants are constants there, and they simply, this output actually is simply depend upon the intermediate keys that are spit out of the key scheduling algorithm along the way. So of course the plaintext is known exponent of subscript. Again, 5, but unfortunately, this expanded version of this, even the 5 rounds there, contains 2 to the power 25 terms, which is really large. And even for 10 round AES, a cryptanalyst could use for each intermediate byte 2 equations of type 1, which I showed you to you. And that will have about 2 to the power 26 unknowns and 2 to the power 50 terms. Unfortunately, we haven't been able to even, put this in practice, so we don't know. But I think it's interesting. It's interesting to take into consideration because it must be, it was a side of AES, and not only, that one it was of AES, but this method can be applied to other block ciphers, and these algebraic methods have to be taken into consideration. Now, I mentioned to you that we don't have, that's why we call linear algebra, not nonlinear algebra, because we only have methods, somewhat efficient methods to deal with linear systems. Well, what we do sometimes in these algebraic or block cipher attacks, what we do is we take these nonlinear systems and replace them by linear equations, where the core of them is a linear equation or quadratic, mind you. But the quadratic portions of them are easily handled. So, for instance, I claim that this system that is of degree, 5, I think. I don't see anything higher than 5. 5, yeah. 5. So 5, degree 5, I can transform it into an equivalent system by inserting more variables, unfortunately. So that's the expense of inserting more variables by a system that is at most quadratic. So what we do is, there are some ways of doing that, but easily you just take some of the equations, some of the terms that makes it non-quadratic, and replace them by a new variable. For instance, x1 cubed is the first term. So I'm replacing 2 powers of x1 and replace it by a new variable. I have only 3 variables here. I'll call it x4. So x4 minus x1 squared is equal to 0 is the new equation that I have to put in there, and x4 is a new variable. And now this becomes quadratic. And you keep on doing this. But of course, this balloons because you have to insert quite a bunch of new variables and more equations. And of course, the system will balloon. But for quadratic, actually, we have some methods of dealing with that, right? So Ferguson actually used this approach, and Courtois and Piepti actually showed that Reindel can be written as an overdefined system of multivariate quadratic equations, which is about 8,000 quadratic equations with 1,600 unknowns. That's not possible to solve it. They used sparse linearization method, which was defined by Shamir and others, but they could not actually, break AES, full round AES. But they did use that a baby Reindel cipher, of course, 1 round, 2 rounds. I think even in a master thesis in 2006 or 8, it was done 4 round actually cryptanalyzed. But again, no approach that can do efficiently or even, dented full 10 round, 10, 12, or 14 round AES. However, in 2007, actually, Courtois and Barth, actually, they broke 10 round DES by an algebraic attack using only 1 known plaintext, which was quite an interesting, actually, feat. Now, does this one actually, because it doesn't break AES, but should we just forget about it? I don't think so. I think the problem deserves attention because it displays some side of AES. That's why I put the weakness in quotes there. they may prove useful or not in breaking the cipher, but it still should be investigated when other ciphers are proposed. I do have, and that's the reason I went a little bit faster through this, but I do have a few minutes to show you some alternatives in Euro, for instance, RC4, RC5, RC6. There are modifications of, some of the same idea. I wanted to read this. What I wanted to do is basically look at some of the features in the rounds there. It's a Feisal scheme cipher. It does, split up the sides, and they go and they, combine and all that. But there is the function actually that does achieve its security, and this is, quite nice, is again the one-time pad and the rotation symmetric. So rotation symmetric basically is like the circular matrices, if you are familiar with that, whereas, one of the rows is shifted by 1 by 2. You've already seen in AES the shift row actually transformation that is done in every round, right? So you shift by 1, by 2, by 3. Well, in RC6, one of the proposals there is shifted by a certain number of bits, which is described by the previous right side. So this is basically what is done, and the addition is not done only one-time padded, XOR, exclusive OR, rather is also done modulo to the power W addition. Now you will see in some of the proposals, some of the counterparts, European and not only counterparts of block ciphers, where they actually involve not only additions in bitwise, component-wise, or bytes, rather they combine various operations in multiple structures. So not only again XOR, but also modulo to the power W addition, which is actually is an addition in a ring structure, right? Algebraic ring. So it's a 64. It's sufficiently secure. Blowfish, which was proposed by Bruce Schneier, it's a 16 round, again Feisal scheme. It does use S boxes. It splits up into not only two blocks but another 4 blocks. And the addition is done also in a ring structure, and the boxes are obviously vectorial Boolean functions. So that's Blowfish. The fast data encryption algorithm, FIL-M, it's again a Feisal scheme. I should mention that it's slightly more involved. Again, Feisal scheme, you see that one of the right side is moving unchained to the left side, and it's also combined via some function to the left side, the left side, to reveal the right side there, right? And the last one is just add up the two to make up the left side. So you one last hurrah, if you will, in the eighth step there. Then the output is simply the right side and the left side, which was the sum, right? The function actually is involved. The function f, which is used there, is known. There are 2 boxes that are applied twice. So that's FIL-N. The idea, which was the international data encryption algorithm, again, it's a Feisal scheme. The Feisal scheme, and you will see again multiple operations. You see I have OR dot here, I have O times. They are operations, I probably should mention it somewhere. There are operations in the ring structure, some sort of an addition, made up addition in hex, and a multiplication modulo to the power n plus 1 with 0 associated to the power n in this ring structure. So you see, many of them now involve some multiple operations in different structures, because it was realized that involving multiple structures that are not isomorphic, mind you, there is an equivalent. There is a way to go back and forth, perhaps, in some of them, but they're not isomorphic. It actually does increase the security of the cipher. We cannot, reveal what happens if you go into rounds of the ciphers. And as I've done yesterday, this is basically my time. I am right under the clock. Thank you so much for your attention, and I hope you took something out of the whole presentation. Thank you.
Thank you, Pante, for your talk. Let's see if there are some questions. I'm just looking at the chat box. So there is no question. There is a comment saying great.
Yeah. Well, there is a question.
Yeah, there is a question. Can you explain again about the notion of index of coincidence?
The notion of coincidence.
That is.
So again, the point of that index of coincidence was to by the way, if you need more details on the index of coincidence, actually the organizers can send you the slides that I used yesterday, where I explained in a bit more details. Ultimately, what it does is, for a putative key there, it takes the expectation. I'm not sure if I can display that, but again, I would prefer for you to send me a message in private, as opposed to, because I don't know where my slides are, honestly. But I mean, you know, I can explain to you, obviously, in more details in private on the index of coincidences. It would be nice. I mean, perhaps that's what you're asking. Perhaps you're asking whether you want to compute for whatever language the index of coincidence. It would be nice, actually, to digitize some of the books and publish that. Again, if you look into the Indian literature for whatever languages, you will not see that many computations, and I think it's worth looking into that. As a side project, it's not, you know, a huge amount of work. It's really not that complicated. So every algos get checked against avalanche effect. Yes, absolutely. So another comment or question was, is every proposal checked against avalanche effects? Yes, it does. Again, they may not satisfy a propagation criteria of high order, but they have to satisfy some order of propagation criteria, because, as I mentioned, you cannot have a bias. So people like working in cryptanalysis, they like to use this, and even my friend Shubhamoy Maitra uses this. We were joking around on that. You have a laser gun and you shoot the 7th bit in your key there, right, or in your plain text. You don't really have a laser gun to shoot exactly that position, but we like to think that perhaps in some way you can mess up, you can change one of the bits in whatever inputs, and that basically gives you a handle on the avalanche. What happens if that particular bit or byte or block has an avalanche in the output, and you don't want to have that. Of course, it's much more difficult to say, well, I have a laser gun that shoots in the 7th and the 16th and the 32. So some of the proposals and the attacks are more esoteric and more academic than others. So they don't really work in practice, but we like to, I mean, they could. So that's why we like to check the proposals, the S boxes against avalanche effects. You see, even the 70s actually boxes were immune to avalanche effects. Well, somewhat. They don't satisfy the SAC, the strict avalanche criterion, which was invented by Orbs and Tavares, but they do have actually some avalanche immunity. Okay. Anything else?
Yeah, I have a question. Is IDEA more secure than DES?
AES is if it's more secure than DES?
Than DES.
Yes, absolutely. Absolutely. So DES, as I mentioned to you, DES can nowadays be cracked by any nation state, and even, you know, a medium company for that matter. If you have some time on your hands, you can probably even build up a computer that maybe just a few $1,000s nowadays, specifically designed. Every operation is simply just a check of a DES key on the computer. So you can, DES is obviously more secure. Now, if you're asking about a triple DES, it is still more secure. There are some attacks on AES that actually dent a little bit the brute force, but not significantly. If you have to spend, if the 256-bit keys require 2 to the power, if I remember correctly, 2 to the power 18 or something like this, that's still beyond the capability of any nation state, even a quantum computer. So even a quantum computer may dent it, but I'm pretty certain it will not break it.
Okay, thank you.
Absolutely.
Yeah, there does not appear to be any other question in the chat box.
Pardon?
Yeah, there is no question in the chat box. Only comments are there.
Yeah, I just can I make a comment? I think it is something I mentioned earlier. Yeah, Professor Stanica has said that he can send us the notes and we can send it by email to anybody who specifically requests for them, as long as make it available publicly. So if you're interested, just write to the conference address, and we will we'll try and send it out to you as soon as we receive them from him. So I just want to thank Mante for getting up early in the morning, 6:30 in San Diego, and giving these talks in spite of not being a morning person. So thank you so much. We really appreciate.
Thank you for inviting me, and let's keep in touch, and that's how I started working with SubTouch, right?
Right. Yeah, I know. I'm very happy about it.
So thanks for the organizing a great conference. I mean, I see that a lot of people actually attended even this late talk. Early for me, late for you. So there was a great interest in this conference.
Good.
Thanks to everybody.
Thank you. Bye and good night.
Thank you so much.
People in India. Good day, Pante. Bye, Prakash.